Okie dokie, alrighty. Welcome back. You may have noticed that my voice has got slightly higher and less caramelly, and that's because I am Ciara, not Patrick, and I am going to be taking you through the next section of this course. So for this project, we are going to be exploring Merkle trees and signatures to build our very own airdrop contract. Let me take you through the code and what we are going to be learning very quickly before we get started. So first of all, what is an airdrop? So essentially, as you can see from my awful drawing here, an airdrop in the context of blockchains is where a token development team send or allow people to claim tokens. These tokens can be any type of token, so ERC20s, ERC1155s, ERC721s, but in this section, we will be creating an ERC20 airdrop. These tokens are gifted or given to, usually for free, aside from the gas fees, certain wallets. So normally there's some kind of eligibility criteria, such as having developed on their protocol on GitHub, or maybe they're part of the community or the like. And this helps to bootstrap the project. So usually there is going to be some kind of list of addresses which are able to claim tokens. Let's walk through this code base very quickly. So if you head inside source, then you'll be able to see the bagel token. And this is the ERC20 token that we are going to be airdropping. And it's a very minimal ERC20 token, similar to what we have done before. And then back in source, you can see this Merkle airdrop contract. And this contract is going to be using Merkle proofs to prove that an address is eligible to claim. It's going to implement a claim function to allow people to receive the airdrop. But it's also going to allow anyone to call claim so that allowed addresses can receive the airdrop without paying for the gas fees. But we are also going to implement signatures to prevent people from receiving airdrops that they actually didn't want to claim. So we're going to finally learn what this V, R, and S mean, how to validate signatures, how to create signatures, and everything to do with signatures. We are also going to create some scripts to generate our Merkle tree, to generate the proofs and the root hash, and also to deploy the contracts and interact with them. We will be taking a small segue into, of course, Merkle trees and Merkle proofs, signatures, ECDSA, what the heck does that mean, and also transaction types. So buckle up because this is going to be a big one. I'm going to show you a brief demo on a zk-sync local chain running in Docker. However, you're not expected to run a local zk-sync Docker node if you don't want. So I'm going to run this script just to show you what we are going to be building. So I'm initializing a zk-sync local node. I then deploy my bagel token contract. I deploy a Merkle airdrop contract. I then sign a message to allow someone else to be able to call claim for me and give them permission to be able to call claim so I can receive the airdrop tokens. I then create some initial supply of my tokens. I send it to the airdrop contract to be able to issue to all of the claimers. I then claim the tokens on behalf of the claiming address. So the function is called by another person so that they can pay for the gas using my signature that I created. And then the address receives the airdrop tokens, and we can see a nice little balance here. Now that might sound confusing, but as we walk through things, I hope things will become more clear. So now that we are airdrop experts and we know exactly why we are going to want to airdrop our tokens, let's go ahead and make a project to airdrop our special tokens to some users that we specify. So the first thing that we need to do is to create a repository to create our project into. So I'm going to do a little mkdir Merkle. And you might be thinking right now, what does this word Merkle mean? You may have seen it in the project overview, but we will explain what this means in a second. So then I'm going to navigate inside this repo, and then I'm going to make sure that I'm on the regular version of Foundry rather than the ZK version of Foundry by running a Foundry up. Okie dokie artichoke. And now we're going to open this up in our VS Code. Now you can see that we've got an empty repository and we can run forge init to initialize an empty Foundry project in our repo. We can go ahead and delete these usual files as we have done so, or Patrick has done so every other time. So delete, delete, and delete. And then we are going to make a new file. We're going to call it Merkle airdrop.sol. Oh, airdrop. And then we're going to do the usual spdx license identifier MIT. Pragma Solidity 0.8 and as I'm recording this, the most recent is 25, but I'm going to use 24. And then contract Merkle airdrop like this. So what do we want to do in here? So I want to have some list of addresses. And then I want to be able to allow someone in the list to claim tokens. So I'm also going to need to create a token contract. So I am actually going to create a token called bagel token because I don't know about you, but bagels are pretty good. I am a big fan of bagels. So the very first thing we need to do is we need to create these tokens for people to be able to claim. So we're going to do the very, very same. We can go again, SPDX, license, identifier, MIT, and then we can use pragma solidity 0.8.24. And then I'm going to do contract, bagel token, and then I don't want those comments this time. So what we're going to do is we're going to use OpenZeppelin to create our ERC20 token to airdrop to our list of addresses. So these want to be ERC20 tokens. First of all, I'm going to just run a forge import. Forge install. So the next thing I need to do is I need to install OpenZeppelin. So if we head over to the OpenZeppelin GitHub repo, then you can see the path is OpenZeppelin/OpenZeppelin-contracts. We've done this all with Patrick before. And so we need to install this repo. As always, we're going to be using pinned dependencies. So you can make sure that if you are doing this project, then as long as you're using the same versions as me, then everything will run smoothly. We are going to be using 5.0.2, the latest version. So if we run forge install OpenZeppelin/OpenZeppelin-contracts at version 5.0.2 --no-commit. And we have successfully installed the OpenZeppelin contracts repo at version 5.0.2. In the Foundry TOML, we can just create a remapping. Remappings equals open square brackets. And then we can do at OpenZeppelin/contracts/ equals lib/contracts/contracts. And I think I did a backtick here. I did. That needs to be a single quote. Okay, so let me just check that remapping. Yep, that's all good. So now we have our remapping in place. We can head back to bagel token. And now we need to import ERC20 from OpenZeppelin/contract/token/ERC20/ER20.sol. Thank you very much, Copilot. And then we are also going to import the ownable. Oops, I did have it there for a second. We're also going to import ownable from OpenZeppelin as well, because we want our contract to have an owner so that they can mint tokens to whoever they choose, etc. So our bagel token is ERC20 and ownable. Again, thank you, Copilot. Now we need to have our constructor, and we do want it to inherit from ERC20 like it's saying. We actually also do want a mint function so that we have the ability to mint, but actually we don't want this initial supply. So we do want a mint function, so we do want to be able to mint tokens to people, like the owner to be able to mint tokens to whoever they choose, but we don't want this initial supply. So we can remove that. And so here we do need to pass some constructor params to the ERC20 constructor. And then we also need to pass the message sender to the ownable constructor. And this is just saying that whoever deploys the contract is going to be the owner of this contract. And so that is it. We have now our very, very simple bagel token contract. And so if we head back to our airdrop contract, now in our tests or when we're deploying, we'll be able to use this bagel token. And actually what we're going to probably do is we're going to pass it through to the constructor of our airdrop contract. We're going to want this contract to be adaptable for any ERC20 of our choosing. So we want to be able to pass in whatever ERC20 we choose. Let's say I was the owner of USDC. I want to be able to airdrop USDC to my trusted, loved followers. Or maybe I'm an artist and I have my artist token and I want to airdrop my artist tokens to the holders of my NFTs. I'm going to want a contract that I can pass this ERC20 through. So I'm not going to hard code it. But before we do that, let's just have a think about how we're going to airdrop our tokens to our list of addresses. Now, you may think maybe I'm going to have some kind of address array, and these are going to be like my claimers. And then I'm going to say, yep, this is my address. And then I'm going to make some function claim, which is going to be external. And then it's going to do something like for I, and then it's going to be like blah, 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 like claimers.length. Check some past and address, so address some account, and I'm going to check the account is in the claimers. However, there's a problem with this. The problem with this is that each time someone claims, we're going to have to loop through this array. Now, what happens if this array is super, super long? What happens if I've got hundreds of claimers? You can imagine that the gas to call this function is going to be extortionate. I'm going to have at some point some kind of DOS, denial of service, where someone calls this function and they're going to run out of gas because they're going to be looping through a massive array. So in order to solve this problem, we are going to use Merkle proofs. Now, what are Merkle proofs? Essentially, Merkle proofs allow us to prove that some piece of data that we want is in fact in a group of data. So if we've got some group of data, like a group of addresses all with an allowed amount, is my address in that group of addresses? Merkle proofs enable us to do this. And Merkle proofs come from Merkle trees, and Merkle trees are the data structure that is used here. And now in the next video, we are going to explain this in a little bit more detail because that sounds super duper confusing. So you're going to have to hold tight with me for a second, and we will come back once you understand what Merkle trees and Merkle proofs are, and then we are going to implement it. Name, please.
Gio.
Wait one moment. Let me just look through these 10,000 other names to find your name. Oh, for goodness sake. Let me go back to the beginning again. What's your name again?
Oh, come on, mate, hurry up.
Yeah, it's whatever, you can just go in.
Wait, mate, what's your private key? You don't use a key store?
Seems like I should be using Merkle trees. The problem. How do I verify that some data is in a group of data? And as this example demonstrates, let's say I have a list of names that are VIPs to some club. How do I determine if someone's name is in that list in an efficient and verifiable way? Another example of this is airdrops. An airdrop is where some tokens are issued to multiple addresses, usually for free. And so in an airdrop, you need a list of addresses that are eligible for these free tokens. How do I determine if my address is eligible for the airdrop? Now you may be thinking I could have an array or mapping of addresses in Solidity, and I could just loop through this array of addresses, and I could just check if my address matches one of the addresses in this array. But this can be extremely challenging. Imagine if this list is extremely long, thousands of names or addresses long. As the list of names or array of addresses grows, looping through this array is going to become extremely costly. And at some point, a denial of service is going to occur, in which a name or address cannot be checked due to insufficient gas. So instead, we use a data structure known as a Merkle tree. Now, you may have heard the word Merkle before in terms of Merkle trees, Merkle proofs, Merkle roots. But what are these things and what does it even mean? Let's go through this now. Quick history lesson. Merkle trees were invented by Ralph Merkle. Ralph Merkle was a computer scientist and mathematician and also one of the inventors of public key cryptography. And he invented Merkle trees in 1979. So as I said previously, Merkle trees are a data structure, and Merkle proofs are a way to prove that some data is present in this Merkle tree. But we still don't actually know what this data structure is. What is a Merkle tree? So imagine a tree, and now turn it upside down. So at the bottom, you now have the leaves, and at the top, you have the root. And this is the same with Merkle tree data structures. Each of these leaves in the tree is a piece of data, and then the branches and the root are built by hashing different pieces of data together. This is what a Merkle tree data structure looks like. And at the bottom is the leaves, and each leaf represents a piece of data in our Merkle tree. The root is then at the top, and the root is built by hashing adjacent pieces of data together. Now, this may sound a little bit confusing, but by the end of this video, you should be able to understand what this data structure actually means, how we calculate the root hash, and how we prove that some data is present. So each of the leaves represents a piece of data that's present in our Merkle tree. And this is often referred to as a leaf node. And it's produced by hashing some data, e.g. the string of the name Ciara. So at the bottom, I've got my VIP names, Ciara, Sarah, Bob, and Dylan. To produce the leaf nodes, I would then hash each of these pieces of data, for example, using the keccak 256 hashing function to produce hash 1, hash 2, hash 3, and hash 4, by hashing each of these individual pieces of data. Adjacent nodes, such as hash 1 and hash 2, are then hashed together to produce intermediate nodes. So hash 1 and hash 2 are hashed together to produce hash 1, 2. Hash 3 and hash 4 are then hashed to produce hash 3, 4. These two intermediate nodes are then hashed together to produce the root hash. This may sound a little bit complicated right now, but we're going to go through this again in more detail and how this actually works in practice. Merkle proofs are then used to prove that some data is present in the group of data in the Merkle tree. And this data can be literally anything. So here we have the names of people in a VIP club, or they could be addresses for an airdrop, or they could be transaction data. But the leaf nodes are just any hash data. So to summarize, what is a Merkle tree? So it's actually a type of binary tree where each leaf node represents a hash of some data, and each intermediate node is a hash of its two child nodes, and the topmost node is known as the Merkle root. Let's dig into how this works in more detail and go through this again so we can really solidify the knowledge. So first of all, we have an individual piece of data. For example, the string of the name Ciara. Again, this data can be anything. For example, data 1, which is equal to the name Ciara, is hashed to produce a leaf node hash. In Solidity, we would do a keccak 256 of the name Ciara as a string. And this produces hash 1. And this is equal to OX7C0374, blah, 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 blah. And this is the leaf node hash. We then do that with all of the data in the Merkle tree. So we hash the names Ciara, Sarah, Bob, and Dylan to produce hash 1, hash 2, hash 3, and hash 4. Next, we need to hash the adjacent leaf nodes together to produce the intermediate nodes. So we produce hash 1, 2 by hashing together the hash of the name Ciara and the hash of the name Sarah. We hash together hash 1 and hash 2 to produce another hash. So in Solidity, we would ABI encode hash 1 and hash 2 together, and then we would hash that using keccak 256. And this would produce hash 1, 2. We would then do that again with hash 3 and hash 4 to produce hash 3, 4 in the same way. Finally, we hash together those two intermediate nodes. So we hash together hash 1, 2 with hash 3, 4 to produce a root hash. And again, we do this by in Solidity ABI encoding together hash 1, 2 and hash 3, 4, and then hashing that using keccak 256. And this produces a root hash such as OX6E10 blah 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 for my list of names. Putting this together, we produce the following Merkle tree. But how do we prove that some data is in the Merkle tree? So how do we prove that my name, Ciara, is part of the VIP club? To prove, e.g. the person entering the club or some address is present in the Merkle tree, you need to provide the data, for example, my name, Ciara, and an array of the intermediate nodes required to reconstruct the tree and calculate a root hash. And this is known as the Merkle proof. So, to prove that my name, Ciara, is in the tree, I would need to provide an array of hash 2 and hash 3, 4. So hash 2 is my proof 1 and hash 3, 4 is my proof 2. And my proof is simply an array of these two hashes. I would then reconstruct the tree by hashing proof 1 or hash 2 with the hash of my name. That resulting hash would then be hashed with proof 2 to produce a calculated root hash. This is then compared with an expected root hash to check whether the name is in the tree. This expected root hash would be known by the club owner because they would have all of the names in the Merkle tree. They would then construct a Merkle tree and have an expected root hash, which they could compare with some calculated root hashes by people trying to prove that they are in the Merkle tree. So essentially, this Merkle tree is constructed multiple times. It's constructed once by, for example, the owner of the club to construct the Merkle tree with all of the names in the VIP list and then calculate an expected root hash. Every time someone wants to prove that they are in this Merkle tree, they would have to calculate a calculated root hash using their proofs and the hash of their data, which they could then compare with the expected root hash known by the VIP club owner. Now, because we're using a secure hash function like keccak 256, it makes it practically impossible to have a hash collision where two different inputs produce the same hashes. Therefore, we can be sure that if we produce a matching root hash in the Merkle proof, you know that data really must have been present and part of the original root hash calculation. Now, this sounds super complicated and a little bit theoretical. Let's look at our VIP example in JSON so we can actually see the Merkle tree in practice. So here you can see the inputs to our Merkle tree. These are the strings of the names in the VIP list. We then have an array of proofs, and these are those two intermediate nodes required to reconstruct the tree. We then have the root, and this is that expected root hash, which we would compare with a calculated root hash when trying to prove that some name is in the Merkle tree. We then have leaf, and this is the hash of the data. So kekak 256 of the string Ciara. And we have this for each of the leaf nodes, so Ciara, Sarah, Bob, and Dylan. But how do I actually produce this Merkle tree and produce the Merkle proofs? There are two main libraries that are usually used to produce Merkle trees, and that is OpenZeppelin's JavaScript library and DMFXYZ's Merkle Solidity library. And what these libraries do is they take the data as input, they hash all of the intermediate nodes together to produce a root hash. They then write this expected root hash along with all the proofs and all of the leaf nodes together into an output file, such as the one that we just saw for the VIP list. That JSON file was produced using DMFXYZ's Merkle library, which is a Solidity script. I will leave links down below for these two libraries if you would like to look into how they work, but let's go into how we can implement this into a smart contract. To implement Merkle trees into a smart contract to verify that some data is in a Merkle tree, we can use OpenZeppelin's merkleproof.sol smart contract. Let's click into this smart contract and see how it works. So we will be using this verify function to verify that some leaf that we provide is present in the Merkle tree using the proof and the expected root hash. So verify takes the proof, the Merkle root, and the leaf that we want to verify. Typically, the root will be stored in the smart contract itself, and the proof will be calculated off-chain using those libraries that we mentioned before, and then the proof is then passed as an argument to this function call. This then calls process proof. Process proof then iterates through each element in the proof array. So we start with the leaf node, and each time we iterate through the proof array, the computed hash is updated by hashing it with the next element in the proof. So we first hash together the leaf node with the first element of the proof, and then the output of that is then hashed with the second element in the proof. If we look inside hash pair, we can see that when hashing both hashes together, we will always take the smaller value first. Efficient hash does the actual hashing. This uses assembly. And this is just an efficient implementation of ABI encoding A and B together and then doing a kekak 256 on that, because it just doesn't allocate or expand memory. But you can just think of it as the same thing, but just slightly more efficient. If we jump back up to process proof, finally we'll compute a computed root hash, which we will return to verify, and verify will check whether that calculated root hash matches the expected root hash from the smart contract. Let's look at this smart contract, which uses Merkle proof from OpenZeppelin to verify if a name is present in a VIP club. So this function, verify if in club, takes the string name and a bytes 32 array of the proofs. We then calculate the leaf hash, and notice here that we are hashing the value twice. This is important. We'll go through this in a second, why we want to be doing this. We then have an if statement that uses the verify function on the Merkle proof from OpenZeppelin smart contract, passes in the proof, the root which we stored in the smart contract by passing it through to the constructor. So if we have the owner of the VIP club, they would be deploying the smart contract and passing in their expected root hash to the constructor. We then pass in the calculated leaf node to the verify function call. And then if that leaf node is not present in the Merkle tree, the calculated root hash did not match the expected root hash, then we'll revert with this custom error, minimal Merkle not in club. Otherwise, we'll return true, and they are present in the VIP club. That name was present in the Merkle tree. Now let's go back. Why did we hash the data twice? We hashed this data twice because of what is known as a second preimage attack. A second preimage attack is where an intermediate node is presented as a leaf node and therefore passes the check since that intermediate node is present in the Merkle tree. In a second preimage attack, an intermediate node is represented as a leaf node and therefore passes the checks since it is present in the Merkle tree. Now, if we go back to our Merkle tree diagram, you can see here if we pass in some second preimage attack data, which would be the ABI encoded #1 and #2, so prior to hashing, if we provided that as input to our smart contract, for instance, to the verify function, This would then be hashed to produce hash 1, 2. We could then provide hash 3, 4 as the proof, which would then be hashed together with our hash data to produce the correct expected root hash. And it would pass all the checks, even though this data wasn't actually present as an actual leaf node in our Merkle tree. This attack is only possible if the function accepts 64-byte leaves as input, and this is because this ABI encode packed hash 1 and hash 2, the two leaf node hashes together ABI encoded, will be a 64-byte piece of data. So if, for instance, this leaf node data that the function accepted as input needed to be 64 bytes long for some reason, then this smart contract could be vulnerable to a second pre-image attack. This would mean that the attacker could pass two leaf node hashes encoded together as the input, so before they're hashing. And since in Solidity, hashes are 32 bytes long, the result of encoding the two leaf node hashes together will be 64 bytes long. So you can see in this function verify bad, we accept arbitrary bytes data as input. We then hash that to produce the leaf node. So we could pass in the ABI encode packed of hash 1 and hash 2 as the data, which would be 64 bytes long, since hash 1 and hash 2 are 32 bytes long. And this function would be susceptible to a second pre-image attack. Now, the first way to avoid this would be to avoid accepting leaf node data that is 64 bytes long. But if for some reason your protocol needs to accept 64 bytes long leaf nodes as the data, there is a second way of preventing second pre-image attacks, which actually is just used in all circumstances. That is, as we pointed out before, the fact that we hash the data twice. This is analogous to using a different hash function for hashing the leaf nodes versus hashing the adjacent nodes together. If a different hash function is used or the data is hashed twice when hashing the data to produce the leaf nodes, as when the adjacent nodes are hashed together, we therefore cannot pass two leaf node hashes encoded together as input because the incorrect hash function will be used and the calculated root hash will not match the expected root hash. So if we look back at our Merkle tree diagram, you can see here that the data to the Merkle tree is hashed twice. Got a Keccak 256 and then another Keccak 256. If we passed in the ABI encoded hash 1 and hash 2 as input, this would be hashed twice, when in fact it should be only hashed once. Just note here that even though you're seeing Keccak 256 multiple times in this little snippet, when we actually hash, for instance, hash 3 with hash 4, we are only using Keccak 256 once. Those other instances of Keccak 256 that you're seeing here are when we hash that original data. So if we were hashing this twice, you would actually see 4 instances of Keccak 256, one for each piece of data that was hashed, and then twice for hashing those two hashes together. Since the output of the hash will be different than what is expected, and hash 1, 2 will be different, since it's hashed twice rather than only once, this hash will be different, and therefore the calculated root hash will not match the expected root hash, and the system will not be susceptible to a second pre-image attack. By using the two scripts we mentioned earlier to produce our Merkle trees, these resultant Merkle trees were resistant to pre-image attacks since the data to produce these leaf nodes was hashed twice. So if we look in the DMFXYZ Merkle repo, and we look in merkle.s.sol, which is the script that can be used to generate Merkle trees, and we scroll down to the bottom, we can see that when we are calculating the leaf node data, we take the data and we hash it twice. So any tree that is produced using the merkle.s.sol script from Merkle or the JavaScript script from OpenZeppelin, both of these resultant Merkle trees will be resistant to second pre-image attacks. For more information on second pre-image attacks, I will leave a link to a fantastic article by Rare Skills on second pre-image attacks if you would like to understand more. So when would you use Merkle trees? There are a couple of real-world use cases. The first one, which we've already spoken about, is in airdrops. Merkle trees are used in efficient airdropping to securely and verifiably distribute tokens to a large number of recipients without needing to store a giant list on-chain. In this process, the list of eligible recipients and their respective allocated amounts are hashed together to create these leaf nodes in the Merkle tree. The root of this Merkle tree is then published on-chain in the airdrop smart contract. Each recipient can then claim their tokens by providing a Merkle proof that is calculated off-chain using one of those scripts from the libraries we discussed earlier. Another use case is in blockchains. In blockchains, the block headers contain information about the block itself, and they contain the following fields: the transaction root, the receipt root, and the state root. And these are those Merkle root hashes for the transaction tree, the receipt tree, and the state tree. And these roots are essentially Merkle roots. Well, actually, they're Merkle-Patricia roots. And Merkle-Patricia trees are very similar to Merkle trees, where the root hash is dependent on those child nodes. And if any of the child nodes change, the root hash will also change. Again, I will leave some information down below on Merkle-Patricia trees if you are interested. And finally, Merkle trees are used in rollups. Rollups are a layer 2 scaling solution that increase the throughput of a layer 1 without increasing gas costs. And in rollups, multiple transactions are bundled together to produce a batch of transactions. The root hash of this batch is then posted on chain. So each of the transactions in this batch represents a leaf node of a Merkle tree. Merkle trees are used in multiple places in rollups, including batch roots, as we just discussed, where transactions are bundled and encoded together into a single root hash using a Merkle tree, and the batch root comprises all transactions in the batch. To prove that some transaction was included in the batch, the transaction details, the batch root, and the Merkle proof showing that inclusion path is provided. Another place is state roots. So the rollups pre and post state changes, the state before and after they were included, they are both represented as Merkle trees, known as the state trees. And then these state roots are submitted to the layer 1 chain. And then Merkle proofs can be used to verify some state and prove its inclusion in the rollup. So now, hopefully you understand what Merkle trees, Merkle proofs, and Merkle roots are, when you should be using them, why you should use them, how to use them in smart contracts, and how to create them. To summarize, Merkle trees are just a data structure where adjacent nodes are hashed together iteratively to produce a root hash. A Merkle proof is a way to prove that some data is present in this Merkle tree and is an array of the intermediate nodes required to reconstruct the Merkle tree. And the Merkle root is just the topmost node in the Merkle tree that we can use to compare a calculated root hash with an expected root hash to determine whether some data was present in the tree. And that is everything you need to know about Merkle trees, Merkle proofs, and Merkle roots. Okay, now you understand all about Merkle proofs and Merkle trees, let's go ahead and implement this into our project now. So like I was saying earlier, we are going to want to have a constructor which you can pass in your ERC20 token. Now the other thing that we're going to want to pass in is the Merkle root, because we're going to need it to be able to compare the proofs and the calculated root hash from the proofs for each user when they try and claim. And when we deploy the contract, we're going to want to specify what that list of addresses and what the amounts are that each address can claim. And that is going to be defined by the Merkle root. So we're going to define our constructor right now. So we've got constructor, and then I'm going to have in here bytes32 Merkle root. Then I'm also going to pass in ERC20. Oops, that's not spelled right. ERC20 drop token. And then in here, I'm going to want to save these values as storage values. So I'm going to have bytes32 private immutable Merkle root. And then because this is immutable, I want I underscore. And then in here, I can go I underscore Merkle root equals Merkle root. And then actually I underscore airdrop token, which we need to define, equals airdrop token. So then I've got IERC20 private immutable I airdrop token. And then the other thing we need to do is we need to import the IERC20 interface from OpenZeppelin so that we can use the functions on this airdrop token. Now we need to create a function in order for our users who are in this allow list, which is defined in our Merkle tree, to be able to claim. So we're going to create a claim function. So we've got function claim external. This function is going to take as parameters the address that wants to claim, and this allows other people to be able to claim for us and pay for our gas. uint256 amount, and this is the amount that we want to try and claim. Bytes32 call data, because we need to specify where we want to be saving this because it's a bytes32 array. And arrays, you need to define where they are stored. We're saying this is call data, and we're going to name this Merkle proof. Okay, so we've passed through the account that wants to claim, the amount that they want to claim, and then also an array of the proofs, the intermediate hashes that are required in order to be able to calculate the root, and then we can compare that to the expected root or the actual root. So next we need to calculate, using the account and the amount, the hash, which is going to be the leaf node. And this is because this is what our Merkle tree is actually going to look like. And you can see here, these are the values in the Merkle tree. So you have an address and an amount to claim. And in our claim function, we provided an address that would like to claim and an amount that they would like to claim as well. So we need to calculate the leaf hash so that we can use the leaf hash alongside the proofs provided to calculate a root hash, which we can then compare to the expected root hash, which we provided in the constructor of the smart contract. So let's make that right now. So we've got bytes 32 leaf equals kecac 256 ABI encode packed. We don't want packed, we just want to ABI encode them, account and amount. Okay, cool. So what does this mean? So we've encoded the numbers together, we've mashed them together, and then we have hashed them. So we've made them into one value, and then we have hashed them together. Okay, that makes sense and looks like it should work. But actually, when we're using Merkle proofs, we need to do something very particular, and I'm going to show you that right now. We actually want to hash it twice. So we're going to do a kecac 256 again. But also, before we do that, we need to do bytes.concat first. Now, why do we do this? Why do we do both of these hashes and why do we concatenate the bytes? When we are using Merkle proofs and Merkle trees, we want to hash it twice, and this avoids collisions. So if you have two inputs that produce the same hash, then that's obviously going to be a problem. So if we hash it twice, then we are going to be avoiding that problem. And this is known as a second preimage attack. I will leave some resources in the GitHub repo associated with this section if you'd like to learn more about second preimage attacks. Now, kecac 256 is actually resistant to clashes for the most part, so it shouldn't be a problem, but it's standard to do this twice. So you can kind of just think of this as just like the general way that we encode and hash leaf nodes. And you'll see this again in a second. So now that we have the hash, we have the leaf, we now need to verify the proof. So to do that, we are going to use OpenZeppelin's Merkle contract. So if we head into lib, OpenZeppelin contracts, utils, cryptography, and then Merkle proof, this is the contract that we're going to want to be using. And we're going to call this function verify, which takes in as parameter that byte32 array of proofs, which we passed as a parameter to our claim function, the root, which we've stored in the contract already when we passed it through as the constructor, and the leaf, which we just calculated. And so then it will call process proof, as we were looking at in the other video, and then it computes this computed hash, which is going to be the expected root, and it will compare that. Back up here, we'll compare that to the root that we provided. So if we head back into our airdrop contract, we can now import Merkle proof and use it to verify our leaf. So now to verify it, we need to first verify that the leaf provides a root that matches the expected root. And then if it doesn't, we want to revert. And then we want to say if the Merkle proof fails, so not Merkle proof dot verify, then we want to be reverting. Now I'm actually not going to use this revert message. I am going to revert with a custom error. So we're going to go revert Merkle airdrop, because it's customary to do the name of your contract first. And then we're going to say invalid proof, which basically says if this fails, then revert with this error message. And we need to declare this at the top of our file. So we need to first say down here, before we declare our storage variables, we want to have our error. And I need to have the keyword error here and add a semicolon. Okie dokie. So cool. This now succinctly verifies our leaf. If they have in fact passed this, then we want to continue with execution and we want to be able to mint them the ERC20 tokens. Now, before we actually send the tokens to the claiming account, we first want to emit the event. So we're going to emit claim account amount. We need to add this in as an event claim address account uint 256 amount. And then we want to be transferring the tokens. And yes, Copilot, you are correct. We want to take the ERC20 token. We want to call transfer account amount. Now, what happens if this account doesn't accept ERC20 tokens? What's going to happen? Well, nothing really is going to happen and the execution is not going to revert. So instead, what we are going to do is we are going to use safe transfer, which means that up here, we need to import safe ERC20 from OpenZeppelin. Now, actually, we need to change this import because we're not going to be importing from the IERC20 file, we are instead going to be importing from safe ERC20, which does also contain this interface. And this is going to be utils. So if we now click into safe ERC20, you can see here that it imports the IERC20, which means we can import it from this contract like we are. So we can import it from here. And then also we have this library, safe ERC20. And it says here that it's a wrapper around ERC20 operations that throw on failure. So we are going to be using this safe transfer, which transfers the value amount of tokens from the calling contract to 2. If the token returns no value, non-reverting calls are assumed to be successful. So it basically just means if we can't, for some reason, send tokens to the address, then it'll handle that for us. Going to say using safe ERC20 for IERC20. And this means that we can call the functions defined in here on any variables of this type. So if we scroll back down here, so now rather than transfer, we can do a safe transfer. Great, now let's see if that compiles. Let's run a little forge build, and that was successful. Now our smart contract takes as argument the Merkle root to compare to, and the airdrop token, the token that we wish to airdrop to our users or anyone in our Merkle tree. We then have a claim function for people to call where they pass an account that they would like the tokens to be airdropped to, an amount, and the Merkle proofs. It calculates the leaf hash, which it hashes twice to prevent collisions. It ABI encodes together the account and the amount, and then it uses this leaf alongside the root and the proofs to calculate an expected root and compares that to the actual root to see whether this leaf was in fact in the Merkle tree. If it wasn't, it will revert, and if it was, it will safe transfer the tokens to the account with the value of amount. Now you may be thinking, Ciara, there's a little bit of a problem with this smart contract. Can you think about what that problem might be? So what happens if my account is in the Merkle tree, I'm allowed to claim, I call this function 1, and then what happens if I call it again? Now there's nothing to stop me continually claiming over and over again until I drain the contract of all the funds. So what we need to do is we need to keep track of who has already claimed to stop them claiming more than once. So the way we're going to do that is we're going to declare a mapping of address to Boolean to say whether the address has claimed or not. So we're going to say mapping of address, user or claimer to bool claimed. Oops. And this is going to be private. And this is a storage variable, so we're going to say s underscore has claimed. And now you may think that after we've transferred the tokens, we can just update this mapping. So we can say that s underscore has claimed account equals true. Now this would be wrong, not just because I've spelt it wrong. Now this is incorrect because it doesn't follow the checks, effects, interactions pattern, which means that it could be vulnerable to a reentrancy attack where the function is called continually and the state is not updated to prevent the account from claiming. So what we want to do is we actually want to do that before we emit the event or transfer the tokens. Now this is great. It says it's true, cool, but there's no check to see whether they have actually claimed or not. So now we need to implement a check to say whether they have claimed or not. So we can say if has claimed, revert with not invalid proof this time, already claimed. So we're saying if they have already claimed, this passes as true, then revert with this error message. So now we need to add this error message to the top of our smart contract like that. Thank you, Copilot. Great. Now we are preventing people from claiming multiple times. So let's go ahead and build that again just to check that everything is going as smoothly as we would like. And it compiles. Great. Now, before we start testing our smart contract, the other thing we want to do is we just want to add some quick getter functions because we have some private variables here that we want to actually be able to read. So I'm going to add in a function, get Merkle root. That's correct. Thanks, Copilot. And then we're also going to want another one, which is going to be function get airdrop token so that we can see what the airdrop token address is. Fantastic. Now let's go ahead and start testing. So if we create a test file, we're going to call this Merkle airdrop t.sol, and then we're going to do spdx license identifier MIT, pragma solidity 0.8.24. We need to import the test contract from the Foundry standard library. So forge std/test sol. And now let's actually add in the remapping in the Foundry toml. So we can go in here, do a little comma, and then we can go forge std equals lib /forge std/src/. And now we can make a little contract. So we can go contract Merkle airdrop test is test. And we're going to write a very quick test to test that our functionality works as expected. Now, in order to be able to do this, we need to set up our Merkle tree, and we need to be able to calculate the proofs and the root. So we need to create two scripts. The first script needs to create the input file. And now this is going to look like this file, input.json. So we're going to create a JSON file, which includes these types. So this is the data types inside the Merkle tree. So we've got address, which is the address it's going to be able to claim, and uint, which is like a uint 256. So it's the amount that the person is going to be allowed to claim. So we have a count of 4, which means that there are 4 leaf nodes, and then the values inside those leaf nodes. So we will be hashing these values. Well, first we'll be encoding together and then hashing these two values together. And we've got 4 different nodes. So these are the different addresses they're allowed to claim, and then their associated amounts. Now, the second file that we are going to need to produce is going to be this output.json. And this output file is the Merkle tree. So it contains all of the leaf nodes, all of the proofs, and the root hash. You will have the input, and then the proofs associated with that input, the root hash, and then the leaf hash. So this is the hash of these two pieces of data. And then this is the root hash. And you'll see that for all of the different leaf nodes, all of the different inputs, the root is the same, because obviously they are part of the same Merkle tree. Therefore, they're all going to be hashed down into the same root for that Merkle tree. So the first file we're going to create is going to be called generate input. And this file is going to create the input JSON file to create our Merkle tree with. So this will contain the eligible addresses and their corresponding amounts they can receive. Apologies if my spelling is a bit atrocious there. I do not have a spell checker here, so hopefully you can understand. And then the second script that we're going to create is going to be called make Merkle. And this script is going to create our Merkle tree. So we'll create our Merkle tree using the input file generated by generate input. And this will create the hashes, the intermediate hashes, and the root hash. And it will also create an output file that contains all of the leaf hashes, the intermediate hashes, which are actually just the proofs for each leaf node, and the root hash. So who is going to be actually in practice calling these two scripts? Now, these scripts are going to be called by the deployer of the Merkle airdrop. So whoever is performing the airdrop, probably the owner of Bagel token, or maybe it's some protocol owner or whatever. So whoever is going to be airdropping tokens to all of their users, or whoever it is that they're airdropping to, is going to be calling these scripts. They are going to run generate input, so they can generate an input file to make a Merkle tree with, so that they have all of the proofs and the hash needed, so that they can then publish this for eligible recipients to be able to obtain their proofs. And usually in practice, yes, this is published for people to be able to obtain their values, or it is built into a front end so that when someone tries to claim the airdrop, the proofs will be injected through the front end. But this make Merkle file is going to generate that expected root hash that we were talking about during the Merkle explainer video. So let's go ahead and create those two scripts to produce these two files. Now, to do that, we are actually going to use Merkle from DMFXYZ. So what we're going to have to do is we're going to have to import this into our project, and then we're actually going to be using a script in here. And I'm going to have modified this. So we'll walk through this in a second, what this does, but we're going to modify this very, very slightly. And I will have already done this. So you can get this from the GitHub repo associated with this course, and you can just copy and paste it in, and we'll walk through it in a second. So the very first thing we need to do is we need to do a forge install. And let's just check what the path was. DMFXYZ. DMFXYZ/Merkle --no-commit, because we're going to be using this repo in our script. And our script is going to be producing our proofs and our root. Now, I just want to jump in here very quickly because I forgot to do pinned dependencies, which we always want to be doing to make sure that your code is working correctly. Now, because there is no official release, we are actually going to use the specific commit hash, and that is this one here, 5FECCD1, and I'm just going to copy that. And then if I head back over to my code, then I could just do the forge install from before, and then I can do an @ and then I can paste the commit hash, --no--commit, and then it installs that specific commit hash. Now, the next thing that we need to do, if we close out our lib, is we need to create a script file. So we're going to make a script called makemerkle.s.sol. And also in the script here, I'm going to create a new folder called target. And this is going to be the target files this makemerkle script is going to hit. So we're going to have a new file called input.json, and then a new file called output.json. So this input file is going to contain, as it sounds, the input for our Merkle tree. So it's going to have a list of addresses with an associated list of amounts that those addresses can claim. And it's going to be in the JSON format. And then this file, which is going to be created, by the way, using a script, which again, we are going to be copying from the GitHub repo associated with this course, which is going to be called generate input. This input file is then going to be used by makemerkle to create the output.json file. The output.json file is going to contain all of the leaf nodes, so the hashes of the information in the input file. And for each of those leaf nodes, it will have the associated proofs, so the intermediate nodes that are required to create the root, and then also the expected root hash. And now there's one final script that we are going to be copying, which is going to be generate input.s.sol, which again, we can copy from the GitHub repo, and I will walk you through very quickly. So let's first do the generate input. If you head over to the GitHub repo, then you can get this generate input file and you can copy and paste it in there. So all this is doing is it's setting the amount that we want our addresses to be able to claim. We've got this types array, which is just the types of the values in the tree. So for us, it's going to be an address and an amount. A count, which is the number of addresses that are going to be able to claim. Whitelist, which is just an array of addresses that we're going to be setting as the addresses which are going to be able to claim. We are going to be looping through it, but because this is a script which is not going to be executed on chain, then we don't need to worry about DOS or gas or anything like that. The input path, which is going to print the Merkle tree to, which is going to be input.json script/target, which we just made earlier. And then inside the run function, we set the type of the first type to be address, the second type to be uint. And then we have 4 addresses, which are the addresses that I am saying that I would like to airdrop my tokens to. The count is the number of addresses, so it's the array, the length of the array. And then I'm going to call this create.json to create the input file, which basically just concatenates a load of strings together with the variables such as the addresses, the amounts, and creates the input file structure. So we set that to the variable input, and then we write file to the input path, the input that we just created, using this cheat code write file, and it concatenates the strings together. And then this is just the root of my project. And then this is the specific file that we want to be writing to, and then we log that we have done this. So if we save that, we can then run it. So if we run forge script, generate input, s.sol, generate input, if we've done it correctly, then it should work. And it won't work because I haven't said the path correctly. So this is going to be script/generate input.s.sol. And you will now see this little error. Okay, the path script/target/input.json is not allowed to be accessed for write operations. Huh, that's annoying. How come we can't write to files? Now, this is easily rectified. If you just head into the Foundry TOML, then you can just set in here the FS permissions. So FS permissions equals, and then we do an array, and then we say in here, then we want to be able to say we can read and write, and then the path of all of the files that we want to be able to read and write to is just the root of our directory. And now we're saying that we can read, the scripts are able to read and write to anything in our directory. So now if we go ahead and run the script again, we have an issue. What's the issue? We forgot our equals sign, need little equals in there. Now if we run our script again, done. The output is found at, so if we head to input and then we go Control-Shift-P, format document, then you can see that we've got the types in the Merkle tree, the count, which is 4, the values, which is the addresses with all of the different amounts. We now have the structure for our Merkle tree. Now, if we head back to make Merkle.s.sol and we copy the make Merkle script from the GitHub repo associated with this course, which has been modified from that Merkle GitHub repo. And actually, we are using Merkle in this file. So we've got this Merkle from Merkle, and you'll see that we've got some squiggly lines under Merkle, which basically means we need to add it to our remappings as per usual. So comma, and then we've got Merkle equals lib/Merkle. And now if we head back to our make Merkle, these should go away. So we've added the remapping into our Foundry TOML. I'm not sure why it's still squiggly, but if we run forge build, then there's no issue so far. So we're going to ignore it for now because sometimes VS Code just screws up and shows a squiggle, even though it can actually find the file. So we're going to explain this first, and then we'll run the script and see if it works. I have added in some comments, which are just my thoughts of why we need to do things. So first of all, it does this using std JSON for string, which enables us to use the JSON cheat codes for strings, which we'll do shortly. We then create a new instance of the Merkle contract from Merkle. So if we head into Merkle, then we can see that what it's doing is it's creating these hash leaf pairs. So it creates, and as it says here, it creates the proofs and verifies. So the first thing we need to do is we need to then define the input path, which is where we just made our Merkle tree, and then the output path, which is where we're going to print the proofs and also the root. And then this elements basically just reads that input file. We're then getting the types from the JSON using the cheat code, read string array, which is why we needed this std JSON. And then we are reading uint to get the number of leaf nodes. So this is count. We then declare some arrays. We've got bytes 32 leaves. We've got a string array inputs and a string array outputs, and then this string output, which basically just enables us to save all of the intermediate variables to retrieve the output file. Now we've got some helper functions here, get values by index, which just enables us to format the data so that we can print it to the output file and then create JSON entries. Again, just formats some of the data into JSON format. The majority of the logic is inside this function run. So what we are going to do is we're going to loop through all of the leaves. We're then going to declare some arrays again, so the stringified data and then the actual data. So this would be like an address and an amount in a string, but then this would be the actual address and the amount in bytes 32. And then what we're going to do, once we've looped through each of the entries, is we're going to loop through for each entry, the address and the array. So this types.length is like the number of variables in, so if we had like an address and 2 uints, then it would be 3 and j would go from 0 to 2 because it's j less than types.length. So when we see an address, we're going to do this read address to get the value. So we get the value of the address. And then because you can't cast straight to bytes 32 for an address, you first need to cast to a uint 160 and then a uint 256 and finally a bytes 32. This is just a standard thing for if you're casting an address to a bytes 32. And then we save that in the jth element of data. And then we will store the input as the stringified value because this is the actual data in bytes 32, whereas this is the stringified data. And then for all of the others, so the uints, then we want to pass uint to get the value, and then we can bytes 32 that value because it was a uint 256, of course, because we said it was a uint. So then we save that bytes 32 value, which is the amount in data j. So this is going to be 1 for the uint because it's the second value, or 0 for the address because it's the first value. And then we stringify that amount and have it in input. And then down here, as my notes were saying, we create the hash for the Merkle tree leaf node. So this is like address and amount. This data in here, we ABI encode the data. The helper from Merkle ltrim64 returns the bytes with the first 64 bytes removed. And this is because the offset of the encoded bytes, and there's an offset because the array is declared in memory. This is an array, so we need to trim that off. Then we hash the encoded address and amount together. This then turns the bytes 32 to bytes, and then we hash it again. We need to kecak256 hash the value twice to prevent collisions. Then we convert the string array to string using this script helper from Merkle, which basically means that we can have all of the corresponding value inputs for each leaf node. And then finally, once we've done that for each leaf and we have stored the leaf data and also the input, then we can loop through those. So each address and amount, and we can get the proof. So we can use the Merkle contract to get the proof for each leaf. So this takes the whole array of leaves, all of the values, and then this is the specific one that we want. So for instance, the first value, so this would be 0. And then we also calculate the root hash. So we, on the Merkle contract, the Merkle contract, we call get root, which calculates the root hash for all of the leaves. And then we get the specific leaf data and we get the stringified input, so the address and the amount again. And then we generate the JSON output file. So this is akin to if you've used OpenZeppelin, the tree.dump. So it generates an output for each of the elements, all of the leaves, so each address and amount. And then we get all of those string arrays and we make it into array string. So we stringify the array of strings into a single string and then set it to output. And then we write that to the output path finally. Now that is a little bit complicated, and some of that you don't really need to understand 100% how this is working. Essentially, it's just taking in all of the inputs and then using this Merkle contract to get the proofs for each of the leaves, get the root, and then store the actual leaf hash, and then also the input, and then printing them to the output file. So if we run this by running forge script /make Merkle.s.sol : make Merkle. Then it says here, generating Merkle proof for this input. Done. The output is found at output.json. So if we head in here, we go Control-Shift-P, format document. Then you can see here, as we said before, you print the inputs. So we've got the address and the amount, the actual values. This is what we were saying. So this input is that address and amount. You've got the proof for that specific leaf for those inputs, and that's this proof. We've got the root, which we calculated here, which is going to be the same. You can get it. It's going to be the same all the way through the file. And then the leaf hash, which is going to be this leaf, which is just the specific leaf that you're working on, the inputs hashed together twice, as we said earlier. And that's it. So if you want to modify which addresses are going to be allowed to claim, you modify the addresses in this generate input, you'll run generate input, and then you can run make Merkle to produce this output file to get the proofs for each of the addresses and to get the root. And now, finally, we can use this in our test to test that things actually work and to check that these addresses can in fact claim. Now let's continue with writing our test. So if we just get rid of our terminal for a second so that we can see what we're doing. So we're going to want a function to test that users can claim. So function test users can claim. Can me with a eligible address claim the airdrop. So the first thing we're going to want to do is we're going to want to deploy both our token contract and the airdrop contract. So we're going to need to store those in variables, and we're going to need to import the files. So we can import Merkle airdrop from source Merkle airdrop, and we also want to import the bagel token because, you know, everyone wants more bagels. So I'm going to airdrop some people some bagels. Alrighty tidy. Now we need to save them in some variables, airdrop and token, and I'm going to make these variables public. That's not public. Public and public. And then we're going to have a setup function setup, which will run automatically when we run our script. And this is not going to be the correct route. So we've got this token, new bagel token to deploy our bagel token contract, and then airdrop equals new airdrop token to deploy our airdrop contract. And we need to have this route. So let's save that in a variable, which we are going to call, we're going to say bytes32 public root equals, and then if we go into our output file, then you can copy this root here. So if we go back in here, then we can say that the root is that, paste it in. Remember that if you change any of the addresses or any of the amounts, then this root is going to change. So in your example, this root might be different, the proofs will be different, all of the hashes will be different. So remember that if you regenerate the inputs file, you'll need to regenerate the output file, and then your root will be different. And then also, I very cleverly, if I do say so myself, made the first address, this one, the address that was generated from doing a make adder and key of the string user. What do I mean by this? Basically, I created an address user. So we got address user, and then we're going to say, and then we've also got uint256 user key. And then in our setup function, we're going to say, you can also pass through the root here. Now that we have it, we're going to use a little function that we get from Foundry. We're going to say user and user priv key equals make adder and key of user. Now, what this will do is it will create an address and a private key. But the way that it does that is it actually uses this to create the address. It's predictable. So because this user address is the address that's going to want to be claiming, we're going to need to add the user address to the generate input file and then recreate our input and output JSON files so we can get the proofs and the expected root. And we're going to want them to be able to claim, so they need to be in the Merkle tree. So to do that, all I am going to do is make sure that I've imported the console from the Forge standard library, and then I'm going to do a console.log the user address. And then if I open up my terminal and I just run forge test and I make sure I add -vv, then you'll see that I've got this user address, which I can now copy. And then if I head into generate input, I can put that in my array of addresses which are able to claim. Now, because I have sneakily already done this, the address is going to be the same, but I'm going to run through the motions just in case you have a different address that needs to be able to claim and you want to know how you're going to add that to the Merkle tree. So I've added it to the array in the generate input file, and then I need to run these two scripts. So I need to run the generate input script, and then I need to run make Merkle to create first the input and then the output file to add it to the Merkle tree and generate the proofs and the root. So I need to run forge script / generate input.s.sol to generate the input file. And then I need to run forge script / make merkle.s.sol to generate the output file. Now, if we head in here, we can do a Command-Shift-P, format document, and you can see this address is in the input file. And then if we head to the output file, we do the same, Command-Shift-P, format document. You can see we now have, again, the address with the amount that they're able to claim. We've got the leaf, so these two values hashed together, the proofs that we need, the root, and everything that we need to add into our test file. So now the address that we're using that we want to be able to claim is this user, and it is in fact in the Merkle tree. Great. Now, the reason I've used make adder and key will be obvious very shortly. Right now, we're not actually going to be using the private key, but I think it's important to show that you can create an address and a private key, because the other one that we're going to use is just going to be make adder, but we're going to do that later, and that just makes an address rather than creating the private key as well. So now in our test users can claim, the first thing we're going to do is we're going to store their initial balance just to double check that it is in fact 0, and we're going to get the balance of the user, and then we're going to use the cheat code vm.prank to prank that the user is calling the function to say airdrop.claim user amount to claim, and then here, not root, we need proof. So now we need to define these two values, and this is going to be capitals, and this we're actually going to name amount, and they're going to be magic numbers. So we're going to say uint256 amount equals 25 bagel tokens, and because the number of decimals is 18, that's why I've got this here. And then I'm going to say bytes32 array public proof equals, and then I'm going to have an array here. And what I'm going to do is I'm going to go into this output, and then for this input, I need to copy these two proofs and put them into my test file right here. And then I'm going to copper separate them, go back in, get the second one, copy that in, paste that in there, save, and now I have my proof. And now what we can do is we can get the ending balance. Now, remember that vm.prank just pranks the next line. So now it will have already stopped. There's no need to do stop prank. We can get the ending balance, and then we can console log it just because that's nice to do. And we need to make sure that we get the console from the Forge standard library. Just double check that that's an export. Yes, it is. Cool. We can console log the ending balance like this. And then we're going to say it here so that we know what we're looking at. Do a little comma there. And then finally, we're going to assert equal. So assert that these two values that I'm going to type in are equal. So it's going to be ending balance minus starting balance is equal to amount. So I want to check that this amount was in fact transferred to my user. Great. Now we haven't used a script to deploy the token and the airdrop contract, but we can do that and we can modify it soon. Now, when we run this contract, so if we go forge test-vv, we have an issue here. And this is because we first need to store these values as intermediate bytes 32 and then pass them through. So we'll do that right now. So we go bytes 32, proof 1, and then we got same thing equals that. And then we can pass through, proof 1 and proof 2. Let's run this again. And it failed. So interesting. How come it failed? It says ERC20 insufficient balance. So the reason this is failing is because our Merkle airdrop contract needs to hold tokens to be able to send them to the user. Because if we head inside our Merkle airdrop contract, we're doing a safe transfer from this contract to this account. So once we have deployed these two contracts, the first thing we need to do is we need to do token.mint to create the supply, the token dot to the owner of the token, and then we're going to send them amount times 4, which we're actually going to save in a variable. So now we're going to do uint256 because we don't like to have magic numbers inside function calls. So we're going to save this in amount to send equals, and then 4 times amount. Let's change this amount to claim to make it nice and verbose. And then whenever we've used amount, we can do hold options and then click to select both of them. Amount underscore to underscore claim, save. And then here I can do amount to send. And then once I've minted to the token contract owner, which is going to be this contract, then I can do token dot transfer to the airdrop the amount to send. So now the airdrop holds all of the tokens needed for all of the addresses to claim. So now if I save this and I run the test again, I haven't declared amount because I renamed the variable. So amount to claim, and then we run it again. And then because airdrop is of type Merkle airdrop, we need to cast this to an address to make sure that it is the right type for this function call. Amazing! Our test has passed and we have successfully airdropped the user bagel tokens. Yay! Now that we have written our test, let's make a deployment script so that we can deploy our bagel contract, also our airdrop contract, and then we can use them in our test. So let's create a new file in script, if it's going to work for me. New file. We're going to go deploy Merkle airdrop.s.sol. Now you could make this so it just deploys the Merkle airdrop, and then you pass through hard code and address for what you want your token contract to be if it already exists. But for this example, I am going to deploy my bagel token contract, and then I'm going to pass it through to the airdrop contract. And that's just how I'm going to do it for this, but it would be pretty easy to modify it. So as per usual, we go spdx license identifier MIT pragma solidity 0.8.24. And then we need to import the contracts that we want to be deploying. Import Merkle airdrop from Merkle airdrop. We also need to import the bagel token. And then we need to make sure we are also importing script from the Forge standard library. I'm not sure why this is complaining at me, but we'll see if it runs. And if it does, we can just ignore it. And then also we're going to need the IERC20 because we're going to have to make some transfers like we did in the test. So we can go IERC20 from OpenZeppelin contracts. Cool. Now we have all the imports we need. We can go contract, deploy, Merkle, airdrop. Ooh. Airdrop is script, as we do normally when we create a deployment script. I'm going to create a function run, which needs to be external, and it returns both of the contracts that we deploy. So Merkle airdrop, and also the bagel token. And then in here, this is not return, this is returns. And then in here, we are going to return deploy Merkle airdrop, which we are going to implement now. So if we make a function, deploy Merkle airdrop, and it's going to be public returns both of those contracts, the Merkle airdrop contract and the bagel token contract. And then in here, we need to deploy those contracts. So as before, as normal, we do vm.start broadcast. We're going to deploy the bagel token. Then we're going to deploy the airdrop contract. Now here, we are going to need the Merkle root. So we're going to save this in a storage variable, Merkle root, and we're going to declare that up here. Set2 Merkle root equals that. And this you can retrieve from your output file as before. And we pass through the bagel token. Then we need to mint the deployer amount to airdrop. So we need to do token.mint token.owner, which is going to be whoever called this contract. And then we send them amount to airdrop, which we need to define. UF256 amount to airdrop is 25 bagel tokens. And we need to actually send them, we need to send the contract 4 times this because there are 4 people who are going to be claiming. So this actually shouldn't be amount to airdrop, it should be amount to transfer. Let's change that to transfer. Cool. And then once we've minted it to the contract owner, we need to transfer it to the airdrop contract so that it is in the contract to be able to be claimed by the claimers. And then we can stop the broadcast, vm.stop broadcast, and then we can return the contracts. And that's it. That's how we write our deployment contract. So now if we go back into our test, we can use this in here now. But what we're going to need to do in order to be able to do that is we need to install Foundry DevOps. So we need to go forge install, and let's just check the path of it. So it's Cyfrin/Foundry-DevOps. So forge install Cyfrin/Foundry-DevOps. No -commit. And this enables us to get the most recently deployed contract, and also means that we can do some ZK Sync special stuff. Okay, now in our setup, we now need to check whether the chain is a ZK Sync chain. If it is a ZK Sync chain, we still want to be doing all of this. If it's not, then we want to be using our deployment script, because as of recording right now, you can't use scripts to deploy in ZK Sync environments. So ZK Sync local nodes, ZK Sync Sepolia, or ZK Sync mainnet. Now, the other thing I want to briefly mention here is that it is completely optional to work on ZK Sync. If you didn't want to work on ZK Sync, you would simply not implement the if-else statement, and everything in the if you would just put in your setup function. This will make sense in a second, but you won't have to have the if ZK Sync logic. You can just purely use your deployment script in your test. So within Foundry DevOps, we have this nice little helper, ZK Sync chain checker, from this path, and this basically just checks whether the chain that you're working on is ZK Sync or not. And then we can just inherit that from our test. So we can go ZK Sync chain checker and test. And then in our setup, we can say if not is ZK Sync chain. Oops. So if you're not working on ZK Sync, then deploy with the script. Else, we're on a ZK Sync in chain, and we want to be deploying as we were before. So to deploy with the script, we need to import this script to this contract. So we need to say import deploy Merkle airdrop from script/Merkle airdrop.s.sol. And then we can say deploy Merkle airdrop deployer equals new deploy Merkle airdrop. And then we can say airdrop token equals deployer.deploy Merkle airdrop to call the function. And that's it. So now if we run our test again, we are not working on a ZK Sync chain. We're currently just testing in a normal environment, in the test environment, and our test passes. Amazing. We have now tested our deployment script. This contract, you may have noticed, allows other people to call claim for another account. I could call claim with Patrick Collins' address, and he would receive these tokens, whether he wanted to or not. So maybe we want a way for these accounts to be able to say, yes, I want this airdrop, or no, I don't want this airdrop. Now, what we could do is we could remove this account and just use message sender throughout, which would mean they would have to call with their own account and they would have to pay for their own gas fees and everything. And that would work and would mean that no one else can claim for them. They can't receive anything that they don't want. But maybe we still want other people to be able to pay for our gas. Maybe we still want other people to be able to call claim for us, and we want to be able to receive the airdrop. So we need a way to be able to say, for me to be able to say, hey, Patrick, here you go. Here's permission to call claim for me. You can pay for my transaction fees. Thank you very much. And I will receive the airdrop because my account is in the Merkle tree. I'm allowed to be able to claim, but I don't want to call claim it myself. So I don't want message sender to be in here, but I still want to be able to receive the airdrop and I want you to pay for me. So the way that we are going to do that is by using signatures. We are going to have a message which essentially says, yes, you can claim for me. And I'm going to sign it with my account and my private key to say, here you go, Patrick. Here's this message that I've signed using my very own signature to say that you can claim for me. And then he can call claim, and then claim will check, is this signature originating from the account that you are wishing to claim for? If yes, are they in the Merkle tree? If yes, then they can claim the airdrop. So to understand how to implement this, we need to backtrack a second and we need to understand what are signatures and how do we implement signature verification into our smart contract? How do we check that the signature was signed by the intended signer by this account? So let's explain that very quickly now. Have you ever heard of ECDSA and ECDSA signatures before? And what are these V, R, and S values? Where do they come from? Everyone just says ECDSA is just some math magic and don't worry about it. And that V, R, and S are basically just the signature. But like, what are they? Really? I'm going to take you through that right now. But don't worry. You don't need to have some crazy in-depth math knowledge. You don't need to have a maths degree to understand this. I'm going to be taking you through things from a high level so we can understand ECDSA signatures, how they work, and what the heck V, R, and S are. Let's get into it. ECDSA stands for the Elliptic Curve Digital Signature Algorithm. Bit of a mouthful. And it's based on elliptic curve cryptography. Don't worry, we'll go through what that means in a second. But it's used to generate keys, authenticate, sign, and verify messages. But first of all, what actually are signatures? Let's do a brief explainer. Signatures provide a means for authentication in blockchain technology, allowing operations such as sending transactions to verify that they have originated from the intended sender. Proof of ownership in Ethereum is achieved using public and private key pairs, and they are used to create digital signatures. Signatures are analogous to having to provide ID to withdraw from the bank. They're kind of like a digital fingerprint, and they are unique to you, the user. This public-private key pair is used to verify that the sender is the owner of the account. This is, of course, known as public key cryptography and involves asymmetric encryption, which sounds confusing, but more on this later. The private key is what is used to sign the message and is used to derive the public key. The public key is used to verify the owner knows the private key. It is extremely difficult and we can assume impossible to derive the private key from the public key, even for a computer, ignoring quantum computing, but don't worry about that right now. And this means that knowledge of the public key does not grant access to the account. This is why if you share your private key, that is a big problem because you can access the account. But if you share your public key, then you're fine. If I give Patrick Collins my address, he can't steal anything. These public and private key pairs define Ethereum externally owned accounts, or EOAs, and they provide a means for interacting with the blockchain by signing data and sending transactions without others being able to access accounts they do not own. An Ethereum address is used as identification and is the last 20 bytes of the hash of the public key. But how do we create public and private keys? How do we create signatures? And how do we verify signatures? Let's now dive into ECDSA, how it works, and what it is. ECDSA is a signature algorithm based on elliptic curve cryptography, and it is the cryptographic algorithm used to do those operations we were talking about. Create keys, create signatures, and verify signatures. And we need to understand how they work from a high level in order to be able to implement these things into our smart contracts and ensure that they are secure. The specific curve used in ECDSA in Ethereum is the SecP 256K1 curve, and it was chosen for its interoperability with Bitcoin, its efficiency, and security. And as with all elliptic curves, it is symmetrical about its x-axis. Therefore, for every coordinate on the curve, there exists another coordinate at the same x point. And each point on the curve is your V, R, and S. They are the coordinates of the points on the curve. Each point is a unique signature. Now, for every X coordinate on the curve, there exists 2 valid signatures, which means that if a malicious actor has access to one of those signatures, even without the private key, they can compute the second one. This is known as signature malleability, which is a form of replay attack. Resources will be left down below if you're watching this on YouTube, or in the GitHub repo if you're on Updraft, if you would like to learn more about replay attacks. Now, there's a couple of constants that we need to quickly define associated with the SecP 256K1 curve. The first is the generator point, G, and is just, we can assume, random point on the elliptic curve. It's purely a constant. The second one is N, which is the order of the subgroup of the elliptic curve points, and it's generated by G. And all you really need to know about N is that it defines the length of the private key, and it's a prime number. Now, it's not crucial to understand what these constants mean. We purely just need to remember that they are constants. They are just constants that are going to be used in subsequent calculations. ECDSA signatures contain 3 integers, and they might be familiar to you: V, R, and S. Therefore, signatures can be denoted as VR and S. R represents the X point on the elliptic curve, based on some random point capital R on the curve, but it's just the X coordinate. S serves as proof of the signer's knowledge of the private key and is calculated using a random constant K, which ensures that the signature is unique every time. V is used to recover the public key from R and represents the index of the point on the elliptic curve, whether the point is in positive Y or negative Y. This is known as the polarity. Let's now go through how public and private keys are generated. The private key is generated as a random integer within the range 0 to n-1, where n is again the order. The public key is an elliptic curve point, calculated by timesing the private key with the generator point. But how do we know that ECDSA private keys are secure? This is because of the complexity of the elliptic curve discrete logarithm problem, which basically says that if we times 2 big integers together, the output being a giant integer, using just the output, we cannot feasibly calculate the inputs. Since point arithmetic in a finite field does not support division, a computer would instead have to use brute force to determine P, even though G is known. And this involves trying every possible value of P to find the correct value, which is not feasibly possible. Imagine I have 2 large prime numbers and I times them together and I give you this output. Do you think you could calculate the inputs? Unless you're a quantum computer, I don't think so. So we can assume this is impossible even for computers. Now, how are signatures created? Signatures are created by combining a hash of a message with the private key. This combination is done using the ECDSA algorithm. Firstly, using the SHA-256 hashing algorithm, we hash the message. Then, secondly, we generate a securely random number K, the nonce. We then calculate a random number, capital R, which is the nonce times the generator point, and take its X coordinate. This is R, lowercase r, V, S, R. This is the R part of our signature. Using the following formula, we then calculate S, using the nonce, the hash of the message, the private key, the R part of the signature, and the order N. V then defines whether we are using the positive part of the y-axis or the negative part of the y-axis. Finally, how are ECDSA signatures verified? The ECDSA verification algorithm takes the sign message, the signature from the signing algorithm, and the public key, and outputs a Boolean representing whether the signature was valid or not, whether the recovered signer matches the provided public key. This works in reverse of the signing algorithm. We convert the S coordinate back to an R coordinate and verify that the provided R coordinate matches the calculated R coordinate. This is done using the following formula, which is essentially just a reverse of what we did when we were signing. The EVM precompile, EC recover, does this for you in smart contracts. It enables us to retrieve the signer's address of a message that has been signed using their private key using ECDSA. And this is what allows smart contracts to verify the integrity of a signature and retrieve the signer. Using EC recover directly can lead to some security issues. So the first, as we discussed, is signature malleability, where because because the curve is symmetric about the x-axis, there are two valid signatures for each value of r. So if an attacker knows one signature, they can calculate the other one. This can be mitigated by restricting the value of s to 1/2 of the curve. If s is not restricted, the two valid signatures exist, and therefore the smart contract can be vulnerable to signature malleability attacks. However, if you're using OpenZeppelin's libraries, such as the ECDSA library, to verify signatures, then you are protected against signature malleability attacks, as long as you're using versions greater than 4.7.3. For example, as you can see in the code from this Lava Labs Code for Arena audit, you can see the EC recover is being used directly without any checks on S, so there is no restriction, and both signatures would be valid. You shouldn't implement EC recover directly, therefore OpenZeppelin's ECDSA library should be used to validate signatures. Aside from signature malleability, the other issue with using EC recover directly is that if the signature is invalid, EC recover will return the 0 address. Now, if this is not handled correctly in the implementation in the smart contract, then this can lead to issues. So there should be a check in the smart contract if EC recover is returning the 0 address, and then the smart contract should revert. If you're using OpenZeppelin's ECDSA library, then this check already exists, and you're protected against this vulnerability. Now, this was a lot of information, and this may be overwhelming, so well done. Give yourselves a pat on the back for getting through this. If this was confusing to you, or you need to rewatch this video, go read some other articles, immerse yourself in some maths magic, then go ahead, because this is extremely complex stuff, and you're probably not going to get your head around it the first time. But well done, because now you understand ECDSA signatures. We know that ECDSA is used to generate public and private keys, generate signatures, and verify those signatures. And we have walked through step by step how this is done. So thank you for watching. In this video, we are going to go through everything that you need to know about signing and verifying signatures by learning about and understanding Ethereum signature standards. We will be going through EIP 191, EIP 712, and how you can verify your signatures in your smart contracts. Let's jump into it. In order to understand signature creation, signature verification, and preventing replay attacks, EIP 191 and 712 must be understood first. Let's quickly go through why these Ethereum improvement proposals were introduced. When signing transactions, we needed an easier way to read and understand transaction data. Before these standards were created, the following message was displayed in MetaMask when signing a transaction. Pretty ugly, right? Difficult to understand whether what I'm signing is correct. Not what you want to see. These standards meant that the transaction data could be displayed in a nice, readable way. Additionally, EIP 712 is key to preventing replay attacks. Spoiler, the data to prevent replay attacks is encoded inside the structured data. So let's go through these standards now, step by step. Let's first start with simple signature verification and implement it into a smart contract. So if we create a function, getSimpleSigner, which takes a message to sign, and this can be any data at all, preferably the string Ciara is awesome, but it's up to you. Notice here the V, R, and S arguments. These are components of the signature that we're providing. This function, getSimpleSigner, hashes the message and then retrieves the signer using the precompile EC recover, and then returns the result. As I said, EC recover is a precompile, so it's a function that's built into the Ethereum protocol and retrieves the signer from any message using the V, R, and S components of the signature. We then create a function, verifySignerSimple, which then compares the retrieved signer to the expected signer, and then it reverts if they're not the same. This is how signatures work at a fundamental level. Take some hashed message plus the signature of the message, retrieve the signer, and check that the address was as expected. There was an issue with this though. There needed to be a way to send transactions using pre-made signatures, aka sponsored transactions. There will be a future video on account abstraction, so remember this, as this will be important. This was already possible outside of smart contracts. However, there needed to be a way to build this into functions in smart contracts. For example, Bob signs a message, aka a transaction, and gives that signature to Alice. Alice then uses that signature to send the transaction, meaning that Alice pays for Bob's gas fees. And so, EIP 191 was introduced. EIP 191 is the signed data standard, and and it proposed the following format for signed data. First off, OX19, this is the prefix, and this just signifies that the data is a signature. The decimal value of OX19 is 25, and this was chosen because it wasn't used in any other context. And due to how Ethereum transactions are encoded, it ensures that the data associated with the signed message cannot be a valid Ethereum transaction. Next, we have the 1-byte version. This is the version that the signed data is using, and this allows different versions to have different signed data structures. The allowed values are 0x00, which is data with an intended validator. The person or smart contract who is going to validate the signature is provided here. 0x01, which is structured data. This is the one that's most commonly used in production apps and is associated with EIP 712, which we'll discuss shortly. And finally, 0x45. Personal signed messages. You then have the version specific data. This is data associated with that version and it will be specified. For instance, for 0x01, you have to provide the validator address. The next section is the data to sign, and this is purely the message we intend to sign, such as a string. Ciara is awesome. Let's now modify our code for EIP 191. The following getSigner191 function demonstrates how to set up an EIP 191 signature. So you can see here we have the bytes1 prefix, which is that OX19. You then have the bytes1 EIP 191 version, and we're using version 0. Then we have the version specific data, so the validator address, which we're saying is this smart contract. And then we have the application specific data, so some message. And we can see it follows that format that we said just a second ago. We then ABI encode this data. We hash it together to produce a hashed message. We then use the EC recover precompile with the hashed message and the signature to recover the signer. As you can see here, retrieving the signer is much more verbose now. As before, we can then compare this calculated signer with the expected signer. However, what if this data to sign, the message, is a lot more complicated? We still don't really have a nice way to display this information, for instance, in MetaMask. So we needed a way to format this data that could be more easily understood. So we needed to standardize this, which was done in EIP 712. EIP 712 structured this data to sign and also the version specific data. This made signatures more easy to read and meant we could display them inside wallets, and also that we could prevent replay attacks. So now the signature has the following structure. We again have the prefix from before and the version. We now have this domain separator, and this is the version specific data. Note that we're working here with 0x01, and this is the version that's associated with EIP 712. The domain separator is the hash of the struct defining the domain of the message being signed. And in the case of EIP 712, the EIP 712 domain looks like this. So you have a struct that has the name, the version, the chain ID, and the verifying contract. This means that smart contracts can know whether the signature was created specifically for that smart contract, because the smart contract itself will be the verifying contract and it will be encoded in the data. So we can rewrite the data as OX19, 0x01, the hash struct of the EIP 712 domain, and then the hash struct of the message. Now we need to define what hash struct is. The hash struct is the hash of the type hash plus the hash of the struct itself, so the data. The type hash is a hash of what the actual struct looks like. So what are the types involved here? What is the name of the struct and what are all the types inside that struct? And then we hash that together to create the type hash. We then create a domain separator struct by providing all of the data necessary. And then we hash together the type hash with all those individual pieces of data by first ABI encoding them together to create some bytes and then hashing that data. But the hash struct is basically what does the data look like and what actually is the data hashed together. Now we have the hash struct of the message. And this follows very similarly. So what is the type of the message? And then what is the message itself? So we have a struct message, which has the member number. So then the message type hash will then just be the hash of the type message uint256. The hash struct of the message then becomes the ABI encoded type hash alongside the actual message struct data, encoded together and then hashed. And this is the hash struct of the message. So we can think of this EIP 712 data as just OX19, OX01, who verifies the signature and what the verifier looks like, a hash of the signed structured message, and what the signature looks like. Putting this together, we then create a getSigner EIP712 function, which first takes the prefix, the EIP712 version, which is 0x01, the hash struct of the domain separator, which we created by hashing together the type hash and the domain separator struct data. We then encode together the prefix, the version, hash struct of the domain separator, and the hash struct of the message. And this combined together is known as the digest. The definition of a digest is just any data resulting after a hash. And you often see it referred to when talking about signatures after you have hashed the message and combined it with all of the other data associated with EIP712. So don't be confused if you see digest in another context. We then call EC_recover with this digest and the signature to retrieve the actual signer. We can then compare that to the expected signer as before in this verifySigner712 function. This may sound extremely confusing, but using OpenZeppelin, a lot of this can be done for us. All we need to do is create the message type hash and hash that together with the message data to create the hash struct of the message. We can then pass this as an argument to the function _hash type data v4, and then this will add the EIP712 domain and the domain type hash and hash it all together to create the digest. So we pass our message through to getMessageHash to do all of that for us, do all of the hashing for us and get the fully encoded EIP712 message. And then we pass that through to our getSigner OpenZeppelin. And this does the same as what we were doing before. So when we were using EC_recover directly, but instead it uses ECDSA.tryRecover from OpenZeppelin. TryRecover then checks the S value of the signature to check for signature malleability and then uses the EC_recover precompile to retrieve the signer. It then also checks if the signer returned is the 0 address, because if the signer is not valid, then EC_recover will return the 0 address and will retrieve the expected signer, which we can then compare to the actual signer that we had to verify the signature. So as mentioned earlier, EIP712 is key to preventing replay attacks. Replay attacks are where the same transaction can be sent more than once, or the same signature used more than once. The extra data in the structure of EIP712 prevents these replay attacks. So that is a lot of information and it may sound super confusing, but I encourage you to try and use this in practice because this is where the knowledge is really going to be solidified. And so to summarize, EIP191 standardizes what the signed data should look like. EIP712 standardizes the format of the version-specific data and the data to sign. So to implement signatures and signature verification into your smart contracts, it's imperative to understand these two EIPs. So now we're well on our way to writing secure smart contracts. This is super confusing stuff, and it took me a long time to get my head around, so don't worry if you're a little confused. This is confusing stuff. Now, before we go ahead and implement this into our smart contract, let's take a little segue into ECDSA signatures. What are those V, R, and S components that we pass through? We said that they were components of the signature, but what actually are they? Let's go into that now. Now that we've learned all about signatures, EIP712, EIP191, ECDSA, and Merkle trees, and we have implemented that into our smart contract, there is one last concept that we have not talked through yet, and we now have all the tools to be able to understand. Do you remember when we deployed our contract to ZK Sync and the transaction type was 113? Patrick gave a brief explainer of what this means, but let's go into this and what the transaction type means and what's actually going on here. If you don't remember, not to worry, we're going to go through it right now. Okay, here we are over in Remix, and I have a smart contract that I wish to deploy. This is in fact the simple storage smart contract back from Solidity 101. Now this could be any smart contract that you want to deploy, but if you remember before, we are going to use the ZK Sync Remix plugin to deploy our smart contract. And then we need to make sure that our environment is set to wallet and that we connect our wallet to the site so that we can deploy using our MetaMask. So the first thing that we need to do is we need to hit compile. To compile our smart contract using the ZK-Sock compiler, click accept. And then when we hit deploy, something very interesting is going to happen. Here we have a signature request. We are in fact not sending a transaction, which we would normally do when we deploy a smart contract. Instead, we are signing a message. Sign this message. So here we have the information to do with the message, and it's broken down all nicely for us. What does this kind of tell you? The fact that we have all of this lovely, amazingly laid out information for us. It kind of tells us that it's EIP 712 message. And here you can see that the transaction type is 113. Hey, that's pretty cool, huh? How come we were in Remix and we expected to do a transaction, but instead we're signing a message? So if we hit sign, then you can see here the information in the terminal that we just signed. So how was that possible? In order to understand this, let's go through some transaction types on Ethereum and ZK Sync so that we can understand this type 113 transaction here. When sending transactions throughout this course, you may have noticed something called transaction types. For instance, when we deployed a smart contract on ZK Sync using Remix, we signed a message which contained the transaction type 113 in the message. Additionally, we added the -- legacy flag when we deployed our smart contracts with Foundry ZK Sync. You may also notice on Etherscan or ZK Sync block scanners the attribute transaction type on all of your transactions. And in this example, it says transaction type 2. Let's go through and break down all of the different transaction types and what this means. Ethereum and ZK Sync share 4 transaction types. First, transaction type 0, legacy transactions. When we added that -- legacy flag, we were specifying transaction type 0. This was the Ethereum transaction type before Ethereum transaction types were even introduced. And it was the very, very first transaction type. Secondly, we have transaction type 1, 0x01. There were some contract breakage risks associated with EIP 2929 and EIP 2930 optional access lists solved this and introduced transaction type 1. And this contains the same fields as legacy transactions with an additional access list parameter, which contains an array of addresses and storage keys. And this enables gas savings on cross-contract calls by pre-declaring the allowed contracts and storage slots. The next transaction type was introduced by EIP 1559, and this is transaction type 2 or 0x02, and it was introduced in Ethereum's London fork. And this transaction type aimed to tackle high network fees and congestion, and it was all around gas fees. Legacy transactions had the gas price parameter, and this was instead replaced with a base fee, which was modified for each block. It also added the following parameters: max priority fee per gas, which is the maximum fee the sender is willing to pay, the max fee per gas, which is the maximum total fee that the sender is willing to pay. So like how much extra are they willing to pay to have priority plus that base fee is the max fee per gas. It should be noted here that ZK Sync does support type 2 transactions, but it does nothing with the max fee parameters because gas works a little differently on ZK Sync. And finally, we have type 3 or 0x03 transactions. And this was introduced in EIP 4844, proto-dank sharding, or blob transactions. And this was introduced in Ethereum's Denken fork and provided an initial scaling solution for rollups while their usage was still low, or is still low, depending on when you're watching this. And it introduced a couple of new parameters alongside those introduced in type 0 and type 2 transactions. It introduced max blob fee per gas, which is the maximum fee per gas the sender is willing to pay for the blob gas. So this was a separate market from regular gas. It's like the maximum extra fee for the blobs. And then also it had blob versioned hashes, which was a list of the versioned blob hashes associated with the transaction blobs. The blob fee is actually deducted and burned from the sender before the transaction executes, which means in the case of transaction failure, it's actually not refunded. And in a second, we will go into EIP 4844, proto-dank sharding, and blobs in more detail in Patrick's video. So wait a second for that. But we have 2 more transaction types to go through. And these are ZK Sync specific transaction types. So first, we have EIP 712 transactions on ZK Sync. And these are those type 113 transactions, or 0x71 transactions. And it defines typed structured data hashing and signing. As we know, EIP 712 introduced a way to standardize the version data and also the data to sign so that it could be decoded and understood in applications like MetaMask. Type 113 transactions enable us to access ZK Sync specific features like account abstraction and paymasters. And smart contracts must be deployed with these type 113 transactions. The fields for type 113 transactions are the same as standard Ethereum transactions, plus a couple of additional additional fields. Gas per pub data, which is a field denoting the maximum gas the sender is willing to pay for a single byte of pub data. Pub data is simply the L2 state data that is submitted to the L1, the data that they are sending. Custom signature, which is a field for the custom signature for when the signer's account is not an EOA. Paymaster params, these are parameters for configuring a custom paymaster, so a smart contract that is going to pay for the transaction for us. And also factory deps. So this should contain the bytecode of the smart contract that is being deployed. Now finally, we have type 5 transactions, or 0xFF. And these are priority transactions. And they enable us to send transactions from the L1 to the L2 directly in ZK Sync. And so now we know all of the different transaction types. Before we head back to Remix, here's Patrick, who's going to explain to us all about blobs, proto-dank sharding, and EIP 4844 type 3 transactions.
In a normal transaction, all your transaction data is stored on-chain forever. That shitcoin that you bought, you thought would moon and went to zero? Yeah, everyone can see you did that. Forever. Blob transactions, a new transaction type, aka type 03, however, give you a box to cram in data that will eventually be deleted. Once the transaction is included in a block, it stores everything per usual, but after a short delay, maybe 20 to 90 days, we delete whatever you put in this box. This is known as the blob, which is sort of an acronym for binary large objects. A lot of people have been using the sidecar analogy, with a blob being the sidecar of a motorcycle, the motorcycle being the transaction, and we eventually light the sidecar on fire and throw it away. Blob transactions were included in the Ethereum Dencun upgrade on March 13th of 2024, and rollups have been absolutely loving it. These blob transactions came from EIP 4844, aka proto-dank sharding, which is a really cool name, but it was actually just named after the researchers who came up with this. So why do we give transactions this optional box for them to dump this temporary data? Well, it goes back to Ethereum's biggest issue today, that sending $1 cost me $2. Ethereum right now is crazy expensive. This is due to the blockchain trilemma problem and some other stuff, link in the description. Rollups are the solution that we've come to know to help scale Ethereum so that our transactions aren't this expensive. You can go to ZK Sync, Arbitrum, or Optimism, and you can send that $1 for substantially cheaper than you could on the Ethereum main chain. And we as a community have essentially settled on rollups being the way we're going to scale Ethereum for the next few to several years. The way they work is they essentially execute a bunch of transactions on their own chain, bundle up and compress the transactions into a batch, and submit that batch back to Ethereum. With many L2s processing transactions, you can get a lot more transactions for a lot cheaper because you're compressing all these transactions on all these rollups or all these L2s. Now, when these L2s submit these batches back to Ethereum, Ethereum has to do a little work to verify that the batch of transactions is actually good, and that right there is where the issue is. When Ethereum verifies that a transaction is actually good, it only needs the compressed batch of transactions once to verify that it's good, and then it doesn't care about the data anymore. But before this upgrade, when you submitted this batch of compressed transactions, you had to submit the whole chunk of transactions and permanently stored on every single Ethereum node on the planet. You see the issue there? We needed this data for like a second, and then every single node would have to hold on to it, even though nobody ever cared about that data ever again. It would be like if every single time you passed an exam in school, you had to carry that exam around with you at all times. What's more important than this state bloat is actually the gas costs. If you store a ton of data on Ethereum or any L1, that means every single node has to store that data as well, which requires them to go out and buy more hardware or do more computation. And so if you want to store more data on Ethereum, you have to pay more gas. And since this compressed batch of transactions is still a ton of data that before this upgrade we were permanently storing on Ethereum, rollups had to pay a ton of gas. So the rollups were kind of pissed. They didn't love this, and neither did the Ethereum community. So these rollups essentially said, hey, so like we're the future of Ethereum scaling, but this call data is super expensive. What if we just like deleted it after we validated our transactions were good? We'll post our compressed batch, we'll check that it's good, and then we'll dump it. That way we don't have to pay the cost of storing that data forever. And then we as the Ethereum community went, yeah, that sounds like a pretty good idea. And so the blob transactions were born. So how are blobs used in practice? Now brace yourself, we're gonna get a little technical here for a second. This is an example of a transaction on the Ethereum main chain where ZK Sync actually sent its batch of compressed transactions to the Ethereum L1. If you scroll down in here on Etherscan, you can actually see this new section here called total blobs. And if we click into this, which if we scroll down in here and we click one of these blobs here, we can see this massive chunk of data, like literally absolutely massive, that is not being stored on Ethereum because it was instead sent as a blob and will eventually be deleted. What's cool too is Etherscan gives us this little blob gas used and blob as call data gas here, where it shows you how much more expensive this data would have been if it was submitted as call data as opposed to blob data here. Obviously, it's way, way cheaper for rollups to submit this data as a blob than as call data, which is what they previously would have had to have done. Getting more technical here, what's interesting is that the L1 Ethereum smart contracts have to validate that this batch of transactions is actually good. They have to validate essentially that this blob is good. However, if they get access to the blob and they do computation with the blob, they would have to have access to the blob, which means they would need to store it on chain, which we can't do. So what the hell? And this is where the proto-dank sharders were actually smart enough to see this coming and actually created a new opcode and a new precompile to do some math magic to verify these blobs. They created a new blob hash opcode and a new point evaluation precompile. And with these two new tools, that was all we really needed to do math cryptography magic, which there's a lot of that in Web3. The blob hash will instead essentially grab that whole blob and hash it using some math magic. And we can use this hash actually combined with some proofs that we submit in a function to actually verify that these blobs are good. For example, if we actually open this up in Tenderly and we scroll down, we can see there's this function here called verify blob information that gets called, which does exactly what it says. It's going to verify the blob information. Looking at this function, we can see it takes some bytes call data called pub data commitments. This is essentially going to be some cryptographic proofs that we generate off chain and some other data, and then the list of blob hashes, which we access with that blob hash opcode. And in this function, we eventually call this internal function called point precompile, which is where we send all that data to that precompile to help make sure that this data is actually solid. The exact function that's actually called with this ZK Sync transaction in specific is this commit batches, where it sends a ton of data, including these cryptographic proofs that's going to combine with these blob hashes to make sure that the blob is actually solid. And boom, with this information here, we can now verify this blob, this batch of transactions is actually solid without having to store that massive chunk of data on chain and bankrupting these L2s, which are definitely not making a shit ton of money right now. And we're able to do a lot of this due to the beauties of cryptography. And that's how blobs work. So a quick recap of what blobs are. Blobs are a new transaction type that allows us to store data on chain for a short period of time. We can't access the data itself, but we can access a hash of the data with the new blob hash opcode. And blobs were added because rollups wanted a cheaper way to validate transactions. Now, we showed you a quick example of ZK Sync, but in essence, this is how a lot of these rollups actually work. Quick summary of how the rollups actually validate these transactions. You submit your transaction with a blob along with some type of proof data. The contract on chain accesses the hash again of the blob with the blob hash opcode. It will then pass your blob hashes combined with your proof data to that new point evaluation opcode to verify the transaction batch using some math magic, and boom. To demonstrate how to send your own transaction using a blob, I've actually created a little GitHub repo, link in the description, showing us how to send one of these transactions. First thing you're gonna wanna do is set up a connection to the blockchain per normal, and then just create some encoded text. For example, we're using this as our blob data. Now, the thing is, blobs have to be at least 4,096 words of 32-byte words combined. So we actually have to take this encoded text and combine it with a ton of basically zeros so that we can create this blob. You cannot have a small blob. They're all big. Then what we do is we actually create our transaction object as you normally would. One of the big differences is we're going to change the type of transaction to a type 3 transaction. Normally, you'll see normal type 2 transactions, which is that EIP 1559 transaction, and it's the default transaction now. Additionally, we want to add some blob gas feed parameters to our transactions as well. One of the other really interesting implications of adding blobs is that we've essentially created a new type of gas market, a gas market for blobs, which has a whole bunch of interesting downstream effects. Video for another time. And then finally, we set up a gas estimate, we sign our transaction, and all we do is we add our blob data to a little blob compartment of our transaction. we sign it, and then we send it. If I wanted to run this on a local blockchain, you go just set up Anvil, set up my Anvil chain to run. And for this, I'm using Rye, which is like a Python thing. I would do Rye, run, send blob, actually run this. And we can see two responses here. We can see a transaction receipt right here. And then if we scroll up, we can see the actual blob that we're sending. And yes, I'm scrolling up this whole time. It's this massive object that we send. EIP 4844, aka proto-dank sharding, is this intermediate step in the Ethereum's long tail scaling roadmap, and is a prerequisite to dank sharding, which includes a lot more cool features. Cooler than the name dank sharding too. But rollups are happening now, and we said, hey, rollups are happening now. We need them cheaper now. So the Ethereum community implemented dank sharding. The Ethereum docs actually do a phenomenal job of explaining dank sharding, where it's going, what it's going to look like in the future. So now you understand blobs, proto-dank sharding. If you want to try out sending your own blob transaction, check the link in the description. Thanks for getting froggy with us, and we'll see you next time.
Let's go back to Remix and have a look and see if we can understand what was going on there. Okay, so now that we understand both about EIP 712 signatures and transaction types, what actually is the mechanism or format that allowed Remix to be able to send a transaction for us in Remix? By signing a message. Now, what happened here was it used something called account abstraction. And ZK Sync has native account abstraction, which means it's built into the blockchain. Account abstraction enables users' assets to be stored in smart contracts rather than externally owned accounts. This means that users can use smart contracts as their accounts, rather than something like MetaMask. On Ethereum, there are two types of accounts: externally owned accounts, where you have a public and a private key and a user has to initiate and sign transactions, and then also contract accounts, where the smart contract itself is the account and any arbitrary logic can be implemented. So you can have things like multiple signers or the ability to have other people pay for your gas and send transactions for you. Accounts in ZK Sync era can initiate transactions just like an EOA, but can also have arbitrary logic implemented in them. And so they have account abstraction natively. And since smart contract accounts are fully programmable, this allows various customizations such as signature schemes, having multi-sig capabilities, you can set spending limits, etc. And this is the mechanism that allowed Remix to be able to send our transaction for us by us signing an EIP 712 message. And since ZK Sync has account abstraction natively, my Ethereum address on ZK Sync is automatically a smart contract account. And so Remix was able to send the transaction for us. Do not worry if you do not understand this, because Patrick is going to be going through account abstraction in depth in the next section. So now that we understand all about signatures, how they work and how we can verify them, let's implement some signature verification into our smart contract right now. So the first thing that we're going to want to do when implementing this into our smart contract is we're going to want to pass the signature through to claim so that we can check it. I sign a message to say that yes, you can claim for my account so that I can receive the airdrop. So we are going to want to pass through the V, R, and S components of our signature. So the types are uint8 v bytes 32 r and a bytes 32 s. First thing we're going to do is obviously check whether they've claimed or not already, because otherwise we don't want to check anything else. And then if they have, we want to check the signature. So if the signature is not valid, then we are going to want to revert with an invalid, not proof, signature custom error. So let's copy this and then declare that at the top. So now we have this custom error. So if the signature is not valid, then revert with this custom error. So how do we check whether the signature is valid? Well, let's create a function isValidSignature. And it's going to be an internal function. So I'm going to start with a leading underscore, isValidSignature. And then we're going to want to pass through the account some message, which we'll define in a second, the V, R, and S components of the signature. And then also we only want to revert if this is false. So it's not a valid signature. Now, what is this message? So this message needs to be the digest, which we were explaining in the video earlier. We are going to create this message digest using a function, and we're going to name it getMessage. And we're going to pass in here the account that we are wishing to claim for and the amount that they are wishing to claim. So that is the specific information about their function call. So let's implement that function now, those two functions. So we've got function getMessage to create the message digest. And this is going to take the address, account, and uint256 amount. And it is going to be public so that we can use it later to get messages so that we can sign them. And it's going to be view, and it's going to return the bytes32 digest. And just remember that the digest is just the hashed message. So when you combine all of the data needed for EIP 712 plus the message that you actually want to sign, once that is hashed, that is what is the message digest. So do not be scared by the word digest. It sounds a little bit technical, but that's all it is. And then we are going to return underscore hash typed data v4, which we need to get from OpenZeppelin. And then we are going to kekak encode, hash together, ABI encode to glue these pieces together, the message type hash with the account and the amount. And here we need to make sure that this is a struct, just to be extra verbose. You don't need to do this, but we are going to do so that it's nice and clean. So first of all, we need to declare a struct. So let's create a struct, and we are going to name it airdrop claim, if I can spell. And in here, we're going to have address, account, and amount. And then additionally, we also need to declare the message type hash, which is going to be this hash of the type. So we've got the type hash now. Amazing. So now we can use that in here. So instead of this, we are actually going to say airdrop claim. And then in here, we're going to do named components. And then now we have the struct. So we have the message type hash and the message. We are encoding these together, and then we are hashing them. And then we are passing that as an argument to underscore hash type data v4, which we need to get from OpenZeppelin. So this underscore hash type data v4 is from the EIP 712 contract from OpenZeppelin. So if we scroll down here, then we can see this hash type data v4. So what this function does is it returns the hash of the fully encoded EIP 712 message for this domain. So it sticks on all the extra information to make it EIP 712 compatible. So if we head in here into domain separator v4, and then we go build domain separator. And remember that a domain separator is just a load of unique identifiers which are hashed together. And this produces a kind of cryptographic nonce that helps to prevent cross-chain and cross-app replay attacks. We can see that it's encoding together this type hash with the hash version, the address, which is because we're inheriting from this. Remember that the address this is going to be this contract. So we need to inherit from it is EIP, not 721, 712, so that we're using it. So that we are now inheriting all of these functions and we can use them in our smart contract. So now we have the version and the version specific data tagged onto our message, and it is fully EIP 712 compatible. We now need to make sure we are calling the constructor of EIP 712. And this takes a name and a version. So I'm just going to call this something like Merkle airdrop, and I'm going to say it's version 1, something like that. And now we can use all of the functionality. So this function should behave as expected. Now there's something wrong here. I think I might have too many brackets. Nope, I'm just missing a semicolon. Right, so now the next function that we need to implement is going to be isValidSignature. And this function needs to take the account that we want to check that the signature was signed by, the bytes32 digest, and the signature. So uint8 v bytes32 r. And yes, all of the rest is correct, apart from this line. This is going to be slightly different because we don't want to be using EC recover directly. Internal view returns, this is actually going to be pure because it's not going to be modifying anything. Returns Boolean, whether it is valid or not. So now we are going to be using ECDSA try recover. So we're going to have some parentheses. We're going to go address actual signer that we have recovered. And then we don't need the error and we don't need the signature length equals ECDSA recover from OpenZeppelin. And we pass through the digest, the V, the R, and the S. And then we return actual signer equals this account. So now we need to import the ECDSA library from OpenZeppelin so that we can use this function. And all this function is doing, again, it's recovering the signer from the signature. And then it calls this internal try recover. And then what try recover does is it checks the signature malleability, which we talked about earlier. So checks it that the S is in fact restricted. And then it uses EC recover to get the signer and checks that the signer is not the 0 address. Like we were saying earlier, we want to make sure we're not returning some erroneous 0 address that we will need to check for. We need to then return the signer. So we return the signer here, which is the actual signer of this signature. And then we compare it against the account. So if we scroll back up here, and here we've got a message error because I've done 721 rather than 712, as per always. So if we scroll back up here, we now do check if the signature is not valid by getting the message digest, passing it through with the account. And we check whether this account is the same as the one recovered by this signature using the digest. And then if it's not valid, we revert. Phew, that was a lot. Let's try and implement this back into our test now. Don't worry if this seems a little bit confusing. I'm hoping that by going over things in the previous lesson and then seeing this again implemented, this might be starting to come together and make some sense. But what we've basically done is we've implemented a signature so that someone else can call claim with our address. And we give them a signature to say, yes, you can claim. I would like to receive this airdrop, but I don't want to pay for my gas fees myself. And it enables someone to be able to call this function for us to pay for our gas fees with our permission. So let's implement this into our test right now. Okay, so now we're back in our test. User wants someone else to be able to claim for them. So we're going to create another address, which is going to call claim. And then user is going to sign a message using their private key. Remember I said earlier, this is why we're going to be using make adder and key, because we're going to use the private key to sign a message to say, yes, you can claim for me. So we need another address. I'm just going to put it up here. Address. We're going to call it gas payer because we're super creative like that. And then we're going to use make adder gas payer equals make adder, which is again just one of those helpful things that comes with Foundry. And we're going to call this gas payer. And then in our test function, we want to prank the user to sign a message, which then the gas payer calls claim using the sign message to send the transaction for them and pay the gas. So we prank that the user signs a message first. So the first thing we need to do is we need to get the message digest. So we got bytes 32 digest equals, and then we can, because we made it a public function, we can call the airdrop contract and we can say get message hash, I think it was called. Did we call it get message hash? No, we didn't, but let's call it, I guess, get message hash because it's more clear. User is the address that we want and amount to claim. So now we have the digest, we can then sign the digest. To do this and get the V, the R, and the S, which is going to be a uint 8V bytes 32 R bytes 32 S equals, we can use the cheat code vm.sign, which will take the private key. So we've got that user private key from before and the digest. So now we have this V at the R and the S. Now when we call claim, we can pass through the V, the R, and the S. Now we need to prank this vm.prank gas payer to make them the person that's calling this function. And now this will all be the same as before. We want to check that the user's balance has in fact increased. So if we save this, open up my terminal again, let's run the test. We now have an incorrect identifier because I changed the name of the function, but then when I used it, I didn't change the name accordingly. So let's run the test again, see if there are any errors. Cannot overwrite a prank until it is applied at least once. We don't need to prank the user because this is just signing. We don't really need them to call it. We've got their private key. So let's run the test again. And it passed. We have now used signatures to say that someone else can claim the airdrop for us. They can pay for our gas fees, and we don't have them sending these transactions without our permission. We are giving permission for them to do that by implementing signatures into our Merkle airdrop contract. This is massive. We have gone through a lot. We have understood Merkle trees and Merkle proofs, and we have implemented them into an airdrop contract. We have then done the same with signatures, understood transaction types. We have then implemented signature verification into our smart contract, and we have tested it. So now, before we make an interaction script and we start deploying to Anvil and to a ZK Sync local node and to ZK Sync Sepolia, I think this is probably a good time to go and take a break. As Patrick would say, go get a drink, go get a coffee, go get some food, go get some ice cream, and let this information marinate. If you have any questions, leave them in the discussions tab of the GitHub repo associated with this course and shoot us with all of your questions so we can answer them. And I will see you very shortly. This section is optional if you don't want to be working on ZK Sync. Now, before we continue, let's just test that all of this works as expected on ZK Sync. So to do that, we are going to run Foundry up -ZK Sync. And this is going to install the ZK Sync fork of Foundry. And once that is done, we can run forge build -ZK Sync to compile our smart contracts using the ZK Sulk compiler, which works a little bit differently than the Sulk compiler. So we need to double check that everything builds correctly for when we're going to be deploying to ZK Sync. Amazing. We've got some warnings here, which normally you should not ignore warnings, but essentially what it's saying is that we shouldn't really use EC recover unless we're sure that the signature comes from an account with an ECDSA private key attached, as ZK Sync Era has native account abstraction. So there may be other accounts which have other signature schemes rather than ECDSA. So we need to make sure that these accounts on Ethereum are not smart contract wallets. They are in fact EOAs, and then they will have a smart contract account on ZK Sync because ZK Sync has native account abstraction, but that's fine. As long as it implements ECDSA signatures and it has an EOA associated with it on Ethereum and it's not a smart contract wallet on Ethereum, then everything should work fine. So we can safely ignore all these warnings, and we are in fact using an interface like ERC20, IERC20, so this warning is also fine. Right, so now if we run forge test -ZK Sync -VV to test on ZK Sync, and it passes. So our tests now pass on ZK Sync as well. Amazing. Okie croaky. So the next thing that we are going to want to do is create an interaction script so that we can claim the airdrop. And what we're going to need to do is we're going to need to sign a message using one account who is in the Merkle tree to say that another person can claim the airdrop for them. And then in our script, we are going to use that signature to claim the airdrop for another account that is in the Merkle tree. To do that, we need to create, of course, an interaction script. So let's create a script inside the script folder called interact.s.sol. And then we shall do the regulars. So spdx, license, identify MIT, pragma solidity 0.8.24. And then we're going to import script from the Forge standard library. And then also we are going to want to get the most recently deployed airdrop contract. And to do that, as per usual, we are going to be using the DevOps tools from Foundry DevOps. So we can go import DevOps tools from, not the Forge standard library, from the foundry-dev/source/DevOps tools. Cool. So the other thing I noticed earlier was that we had a little lib / here, like this, and I just went ahead and removed it. And then in my Foundry TOML, I just added this line to say foundry DevOps / equals lib / foundry DevOps / so that I didn't have to say lib every time. You could have left it as is and added lib here, but I wanted to do it like this. And the other thing we're going to need is we are going to need our Merkle airdrop contract so that we can call claim. We need the ABI, so we're going to need it. I'm going to call it claim airdrop is script, so we have all the script functionality. Then we can create a function run to run the script. Make it external. And then in here, we are going to want to get the most recently deployed Merkle airdrop contract. So we've got an address, most recently deployed, same as usual, equals DevOps tools dot get underscore most underscore recently underscore recent underscore deployment. And then in here, we need the name of the contract, which is just Merkle airdrop. And then we need the chain, which is going to be block.chain ID. And then we need to pass this contract address through to a function, which we're going to create in a second. So I'm going to call my function claim airdrop, and I'm going to pass through the address. Let's now create that function. So we can do function claim airdrop, not with a capital, the lowercase c, which is going to take an address. We're going to call this airdrop, make this public. And then in here, we're going to want to call claim. So we need to wrap the address in Merkle airdrop, the interface, so that we can get the function. We can get the function signature so we know what things to pass through. Then we can call claim. And then in here, we're going to need the claiming address, which is the address who's going to be receiving the airdrop, the claiming amount, the proof array, and the V, the R, and the S components of the signature. We're also going to want to do a little vm.start broadcast as per usual, and then vm.end broadcast. Let's try and declare some of these variables. So we're going to do an address, claiming address equals, and I'm going to make this script work for Anvil. You could switch it out, this claiming address, for whoever is going to be signing the message, but I have in this input file made this second address the default Anvil key so that we can sign the message and run the end-to-end flow on Anvil. You could switch this out for whatever address you have that you want to be claiming the airdrop, and then in your interaction script, you're going to want to put that address there. But we are using the default Anvil address. So now we have the claiming address. Now we need to have the claiming amount, which is going to be 25 bagel tokens, and it has 18 decimals. And now we need this bytes 32 array proof. So as before, we need the bytes 32 proof 1, and then we're also going to need the bytes 32 proof 2. And both of these things, again, like with the test, we can get from the output. So if we find the address input, it's this, then these are the two proofs. So if we copy the first one, chuck it in there, and then we copy the second one, and then we chuck it in there. Great. Now we need to set them to proof. So we need to put them inside the array. So we're going to have proof 1 and proof 2 inside the array. And now we can pass this through. Great. Okay, so what about this VR and S? Okay, so to get the VR and S, we need to sign the message using this account, the account that we want to claim. They are going to be, in this demonstration, different from the account which is going to be calling this script, is going to be running this script and calling claim. This account, the default Anvil account, can receive the airdrop for free. So we need to give them permission. So that means we need to sign a signature. There are a couple of ways with Foundry that we can sign signatures. The first one we have already seen, and that was when we used this vm.sign. And we could create another script in which you do another vm.sign, and that would work perfectly fine on Anvil or any chain in which Foundry scripts run correctly. So it wouldn't work for ZK Sync, for instance. At the time of recording, you cannot run scripts correctly on ZK Sync. And the other reason is because maybe you don't want to be creating a script. Maybe you're just interacting with a protocol and you just want to be able to create a signature quickly. So I'm going to show you another way that we can create signatures, and that is using cast wallet sign. And what this command is going to do is it's going to create us a signature, which is going to have the VR and S components all together. It's going to be one bytes object, and then we're going to have to break it down into the VR and S components. So let's go ahead and first create our signature. Okie dokie, let's create a signature using the default Anvil key to say that the second default account who is going to be running this script can in fact claim for us. So firstly, to do that, we are actually going to want to get the data to sign. So I'm hoping that at this point you have an Anvil running, an Anvil local node, and you have deployed both the bagel token and the airdrop contract to it. But in case if you have cancelled your Anvil node or whatever, let's run it again. The first thing you're going to want to do is a little Foundry up to make sure that we're on the vanilla version of Foundry, not the ZK version of Foundry. And then you can copy the make file associated with this course so that we can run make deploy. And what this is going to do is it's just going to run our script. Nope, first I need to start my Anvil local node. And then once that's done, I can run make deploy. And then up here, you can see we have the Merkle airdrop token and the bagel token successfully deployed. So now what we can do is we can copy this Merkle airdrop token and we can call on this contract get message hash to get the data to sign. So let's do that now. We can run cast call, paste in the address of the airdrop contract, get the function signature, which is get message hash, and this takes an address and a uint 256, and then we need to put in those two variables. So we copy the address and the claiming amount, and then we need the RPC URL, which is just http://localhost:8545, and now we have the data to sign. So now we can use cast wallet sign to sign this message. And the other thing that we're going to add is we're going to add --no hash so that this command doesn't hash the message again, because sometimes you can use this to sign a message that is purely a string, like Ciara is awesome, and you can sign that. However, because we already have bytes, we don't need them to hash that again. So we can just add this --no hash. And then we paste in the bytes to sign, and then we're going to do -- private key, and then we're going to paste the first default Anvil key private key. Now, if you were doing this on a test net and using an actual address, an actual account, then you are not going to be doing private key here. You're going to instead do -- account, and then you're going to use your key store account to sign the message. So you're not going to be using private key. The reason I'm pasting my private key in here is because it's not mine. It's the default Anvil key that is public. So if we scroll up here in the terminal, in our Anvil terminal, we can get the first default Anvil key. We can paste that in there and we can sign the message. Now we want to copy this message apart from the O and the X so that we can use this signature. We can break it up into the VR and S components and pass it through to claim. When you use cast wallet sign, you create one single signature. However, what we need is we need a V, an R, and an S broken up individually, because that's what our API is taking. We could have designed this just to take a simple bytes signature, which had all of this information, the V, R, and the S, packed together. And the way we would have had to do this is when we verified the signature using this try recover. So you could instead use this try recover from OpenZeppelin, which takes just a signature and then splits it up itself into the V, the R, and the S. And it does this using assembly. So it takes the first 32 bytes and sets it to R, the second 32 bytes and sets it to S, and the final byte and sets it to V. And then it uses the regular version of try recover that we were using before that takes the V and R and S individually. So it's up to you how you want to design your protocol. Do you want your users to be having to provide their V and R and S separately, or just one signature? Different signing methods output different things. So some, including cast wallet sign, output just the byte signature. Whereas if you use vm.sign, it gives you the V, the R, and the S separately. So it's up to you how you want to implement it, but we have chosen to design it with V and R and S separately. And then I will show you how we can unpack a signature into the individual components and how we're going to create signatures in a second. But I just thought it was worth noting that you can do either or, and it's a very easy swap out. Let's split up the signature into the V, R, and S components now. So the first thing we want to do is we want to save this byte signature as a variable. And the way we do that is use the keyword hex, and then you have quotations, and then you plonk the data in there without the OX. And let's just make this private, because we don't want inheriting contracts, inheriting script store to use it. Right, so now in order to be able to pass this through, we need to break it up. So let's create a function that will do that. So we've got uint8, v bytes 32 r, and bytes 32 s equals. Now you might think that you could do like an ABI.decode. However, the signature is not created using ABI encode, but instead it's an ABI encode packed. So all of the V, R, and S, well actually in this case it's going to be R, then S, then V, are packed together. They're concatenated together. Instead you've just got this whole thing is literally just the V, the R, and the S. The first one is R, which is the first 32 bytes. The second part is S, which is the second 32 bytes. And the final byte is V. So we purely just need to break this up to find them. So instead of doing ABI decode, we're going to make a little function called split signature. Then we're going to pass through that signature. Let's create that function now. So we've got a function called split signature. which is going to take a bytes object, call it sig. Let's make it public. Returns uint 8 v bytes 32 r and bytes 32 s. And then in here, we are going to do something very similar to what this Copilot code is saying. So we first need to require that the length of the signature is equal to 65 bytes. And that's because 32 plus 1 is 65. And then that's the length of v, r, and s altogether. And otherwise, we will return with this string, invalid signature length. Now we need to do the exact code that it says here. So we are using assembly to break up the signature into v, r, and s. Now, weirdly, when you have a signature which is combined together, the v, r, and s, r is actually first. So it goes r, then s, then v. However, when you're using functions, so like when you're using OpenZeppelin or you're interacting with an API of some description, it usually follows the format v, then r, then s. It can be a little bit confusing, but if you're using a function, typically it's going to be v, r, and s. And then if you're looking at a signature, you're breaking it up, you're packing it together, it's going to be r, then s, then v. So what this assembly code is doing looks kind of scary, but don't worry too much. We don't need to worry specifically about what all these words mean. This will be covered in depth in a later part of the course. There is actually an assembly and formal verification course, and it will be covered in depth there. But from memory, we are loading the first 32 bytes and then setting it to r. Then we're getting the second 32 bytes and setting it to s. And then we're getting the final byte and setting it to v and returning it. So actually, rather than doing a require here, I'm going to do a custom error. So we're going to say if the signature length is not equal to 65 bytes, then we're going to revert with not invalid signature. I'm going to do _ claim drop script so that we know where the error is coming from. _ invalid signature length. And then let's copy that, add that to the top of our script contract. So we can say error that. And then we can also restrict this to pure. So if you see here the require statement instead of the if and then revert in the rest of this recording, or you see the contract without this error message, just note that I had to make this modification afterwards because I wanted to save the gas. So you should be doing this, not a require statement, and you should have this error at the top of your script. Now we have used cast call to get the message to sign, and then we've used cast wallet sign -- no hash to sign the message. And then we have split up the message into the V, the R, and the S. So now if you ever need to have a signature to interact with a protocol that requires you to have a signature, you can do it both if it's the full signature, or even if you need the V and the R and the S split up separately. You know how to do both, which is amazing. Right, so now that we have done that, we can safely run our script. And hopefully it'll work as expected. So we can run forge script, and then the path script /interact.s.sol : claim airdrop -- rpc-url http : localhost 8545 private -key. Again, this is going to be -- account if you're working on an actual test net or mainnet chain, not on like a local node. However, I am actually going to use this second Anvil key so that I can claim and pay the gas fees for this first one. So the second Anvil key is the one that's going to be calling claim so that the first address is the one that is going to receive the tokens. And then we need -- broadcast. And I think that is everything that we need. So we can run this command and we have an error. I've been silly. This isn't end broadcast, it's stop broadcast. No matter how many times I run scripts, I always forget what the API is like. Okay, let's run it again. Remember, chain ID not found. Have I spelt it wrong? Yes, I have. Missed an I, and then let's run again. And I've also spelt deployment wrong. Deployment. There we go. Again. And we have successfully completed the claim. However, we're going to want to check this. We want to check whether the first address has in fact received the airdrop. So we can run cast call on the token contract. So if we just scroll up, we can retrieve this token contract address so we can get the balance of that first default Anvil address. We need balance of, and this takes an address, and that is the function signature of the balance of function on the token contract. And then the address that we are going to want is the first anvil address. And if we execute that, then we get this horrible looking piece of data. So we now need to do cast --2 -dec to convert this data into decimals. And you can see this is in fact the amount that we airdropped to them. They have received the airdrop. Fantastic. Our script worked. We airdropped 25 bagel tokens to the default anvil address using the second default anvil address to pay for the gas by using a signature created using the first default anvil address. They said, yep, go ahead, use my signature and you can claim so that I can receive the airdrop. And it all worked as expected. Amazing. This section is optional if you don't want to be working on ZK Sync. Let's now do the same thing, but on a ZK Sync local node. So the first thing that we want to do is we want to run foundry up -ZK Sync to get the ZK Sync fork of Foundry. And we also want to kill this anvil node. Now, things are a little bit more tricky and difficult on ZK Sync and ZK Sync local node because we cannot use scripts at the time of recording. So I have gone ahead and made a bash script to run all of the commands. And what we're going to do instead is we're going to run through what the script looks like. I'm going to walk you through what commands it's running, and then we're just going to go ahead and run it. And it's going to be one command. It's going to be super pretty and lovely. Instead, you're just going to understand exactly what commands you are using, and you could then go and do it from scratch yourself. But I don't expect you to write this bash script from scratch. Instead, I want you to copy this from the GitHub repo associated with this course. We're going to create a file called interactzk.sh. And then you can paste in the script, which is called the exact same thing on the GitHub repo. So in here, we have different variables that we need. So we've got the default ZK Sync local key. This is the private key for this address, which is the default ZK Sync account. And this is the account which is going to be calling claim. It's going to be paying for the gas so that the default anvil key, the same address as before, is going to receive the airdrop. So as before, we need the private key so that we can sign the message. And we're going to do that the exact same way as before. Then we also have the root and two proofs. We have the proofs for the default anvil key. So we've got the root and the two proofs, same as before, because we're going to need to deploy the bagel token contract and also the airdrop contract. So we need to pass through the root to the constructor. So the first thing this does is it starts a ZK Sync local node using the ZK Sync CLI. So to be able to run this command, you actually need to have Docker installed and running. So make sure, pause here if you need to do that. And then it deploys the token contract, the bagel token contract, and just prints that to the terminal so we can see what's going on. Then it uses that to deploy the airdrop contract. And it passes through the root and the token address as the constructor arguments. And then it prints that to the terminal again. Then we get the message hash by calling getMessageHash using the default anvil address and the number of tokens that we want them to be receiving. We get the message hash. Then we sign the message, again using cast wallet sign. We get the private key for the default anvil key, the one who wants to be receiving the airdrop. And then we clean that signature by again removing that OX at the start. And then we print that clean signature to signature.txt. We then run a script called split signature, and that is going to do the same as what we did before when we used assembly to split the signature into V, R, and S. And it's going to take the signature from this signature.txt file. And then it will output the V, the R, and the S to the terminal. We will go ahead and create this file in a second. I will loop back to it. So then we need to send tokens to the token owner. So we are creating an initial supply, and we can do that because we are in fact the deployers of the token contract, therefore we are the owner. And then we need to transfer those tokens to the airdrop contract, which again, we can do because we are the owner of the bagel token contract. So we created an initial supply, then we sent them to the airdrop contract. Then we call claim on behalf of this default anvil address, but using the default ZK Sync address. And we pass through the proofs and the signature, as well as the address that we want to be claiming and the amount. Then we get that hex balance by again doing cast call to get the balance of the default anvil address on the bagel token contract. And then we output this to the terminal in a very nice way using cast --2 the same as before. And then we just clean up by removing that file, the temporary file that we did to put the signature into so that we could read it in our script. Let's create that script very quickly now. So we're going to call it split signature.s.sol. And then again, because we've already run through this, you can just go ahead and copy and paste this from the GitHub repo. And this is doing the exact same thing as before. It's using assembly to get the first 32 bytes, setting it to R, the second 32 bytes and setting it to S, and the last byte and setting it to V. And then in run, we are reading this signature.txt file. We're passing the bytes to get it into bytes form from string. And then we are splitting it into V, R, and S using that split signature function. And then we are logging that to the terminal so that Interact can read from the terminal the V, the R, and the S, so that we can then use them when we are claiming. So make sure you have Docker running, and then we are going to run chmod +x interact zk and /interact.sh. And what this is doing is this part makes the script executable. Then we've got and to say we've got another command, and then /, which runs, and then the file, which is interactzk.sh to run the file. Let's enter that. So we're creating a zk sync local node, deploying the token contract with the address, deploying the Merkle airdrop contract with the address. We're now signing the message. So we're calling the function to get the message hash, and then we are running cast wallet sign to sign the message. We're getting the V and the R and the S, and then we can pass it through to claim. We claim the tokens, and then we can see that the balance of the claiming address has in fact increased. It worked. Amazing. Let's finally deploy to ZK Sync Sepolia so that we can wrap all of this up, and then we will be all finished here. Let's do that now. Here we are going to be deploying to ZK Sync Sepolia, but feel free to deploy to whatever rollup of your choosing. Okay, finally, let's deploy to ZK Sync Sepolia. How exciting. We're going to have to do everything from scratch, not using scripts, which I don't actually recommend. I recommend when you're deploying even to a testnet, you don't want to be getting things wrong and wasting funds. So you ideally want to be using a script. So feel free to go ahead and choose another chain where you can literally just run this deploy Merkle airdrop script to deploy the contracts, and then also this interact script to interact with your contract. You can do that from another chain that supports vanilla Foundry, and you can run scripts. But as of recording, you cannot do that on ZK Sync. So I'm going to be doing everything using my terminal instead. So first of all, we need to deploy the token contract. So we can run forge create. There's actually something I wanted to explain very quickly now. The first thing I want to explain is that I'm going to be doing everything using an already imported wallet. I have two wallets in my MetaMask, and I have named them Updraft and Updraft2 as key stores. So I can do -- account, and then I can say Updraft or Updraft2 like this. So what I'm going to do is, because I've already put my account address for Updraft2 that is in my wallet key store in the input here. So this address is actually mine. So it's already saved in my key store, so that I'm never going to be using -- private key. And then the other account that I'm going to be using is Updraft, who's going to be deploying all the contracts and calling claim for Updraft2, which is this address. So forge create, let's deploy that token contract. And then we need the path source / bagel token.s.sol. No, it's not a script. We've been doing too many scripts. .sol bagel token. And then we don't have any constructor arcs, so I can just do --rpc-url curly brace zk sync sepolia rpc url. Now make sure that in your env file you already have this, and you've run source.env to make sure that your command line can see these variables, and you're going to want to use this RPC URL here. As of recording, the Alchemy RPC URL is not working 100% correctly. Maybe when you run this, it could be up and running and work completely fine, but I was having issues, so I'm using this RPC URL. And then we are going to add -- account. And for me, it's going to be Updraft. That's what my Updraft. And that's what my key store wallet is called. It's called Updraft. And yours might be default or default key or something like that. And then we're going to add -- legacy to make it a type 0 transaction, and then -- zk sync. Now, maybe I didn't actually run source.env, and let's run it again. And now I need to enter my key store password for Updraft. I'll go ahead and do that now. So we have now deployed the bagel token contract to this address. Now let's save that as a temporary local environment variable by using the keyword export. And we're going to call it token address equals, and paste it in there so that we can use that later. Now let's deploy our airdrop contract. So again, forge create source slash Merkle airdrop dot sol colon Merkle airdrop. And now we need the constructor args dash dash constructor args. Then we need the token contract, token address. And then we need that root hash, which we can get from our output file. Root, copy it, paste it in there. We don't need to save this as a variable because we're only going to use it once. And actually, this needs to be the other way around. So let's remove that, swap them around because it's the root first and then the token contract. So $token address dash dash RPC dash URL ZK sync Sepolia RPC URL dash dash account updraft dash dash legacy to make it type 0 dash dash ZK sync. Enter your password again. By the way, we don't need to worry about these warnings here. I think I mentioned that earlier, but it's fine because all we need to do is make sure that these inputs, these addresses, are not smart contract accounts on Ethereum. And also because we are using EC Recover, the other thing we need to do is make sure that the smart contract account, which is native on ZK Sync, is using ECDSA signatures. Other signature algorithms can be used, so just be careful on ZK Sync and make sure that the addresses you are airdropping to do use ECDSA signatures and not some other signature algorithm. So we have successfully deployed our contract to this address. So let's again save that to an environment variable. So we can run export airdrop equals and then paste it in there. So the next thing we need to do is we need to get the message to sign. And then I need my account 2, the one that's in the Merkle tree, this OX2EA blah, 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 to sign the message. So we can run cast call airdrop address. Function signature is get message hash. And it takes an address and a uint256. Then the address that we want is going to be this one. This is the one which is going to receive the airdrop. And the amount is this, 25 bagel tokens, dash dash RPC dash URL dollar, ZK sync RPC URL, and that's it. So now we have the message to sign. So now we can use cast wallet sign using my second wallet in my key store, my second account on MetaMask to sign the message. So we can go cast wallet sign. Then we need dash dash no hash like before. Then we need the bytes to sign. Then I'm going to use dash dash account. And I'm going to use updraft 2 to use my second account, the one who is in the Merkle tree and is going to receive the airdrop. So I need to enter my password. So now I have the bytes. I can go ahead and copy that. And then I can go into split signature. And I will need to make a little file called signature.txt. And I need to paste that in there and remove the OX. So I'm just kind of doing what the script was going to do for me. And then that means that split signature can use the signature.txt file to get the signature and split it up into the V, the R, and the S. So let's run this script now. So we can run forge script slash split signature.s.sol colon split signature. And now we have the V, the R, and the S components. Let's save them into variables. So export V equals 27, export R equals, copy this, paste it in there. Export S equals, copy this, paste it in there. And now we can run claim. So we can claim on behalf of account 2. But first we need to create an initial supply and we need to transfer the tokens to the airdrop contract. So let's quickly do that now. So we're going to run cast send. We need the token address. We need to mint tokens, which takes an address and a uint256. And we are going to mint to my address in my MetaMask, the one who deployed the contract, the owner, and then the amount, which is going to be 4 times the amount that each person can claim, so that the contract holds the entire amount that needs to be airdropped. Oops, don't know why I press enter. And then we need dash dash account, and then this is going to be first account, because they are the owner of the contract. Then we need dash dash RPC dash URL, ZK sync, Sepolia, RPC, URL. And the transaction has been successful. So now we need to send those tokens to the airdrop contract so that it can perform the airdrops. So we can run cast send. We're almost there. We need the token contract. We want to run transfer, which takes an address and an amount, uint256. Then we want to send to the airdrop address. And we want to send them 4 times the amount that each person can claim, because there are 4 claimers again, and then dash dash account. And then it's going to be for me called updraft. But this is whoever you have been deploying all the contracts with and the person who's going to call a claim. --rpc URL. ZK sync, Polia, RPC URL. And we've now transferred the tokens to the airdrop contract. So let's call claim. Let's use our first account to claim for our second account, where the second account is in the Merkle tree. I know it sounds like I keep repeating this, but I feel like it could be a little bit confusing, so I just want to keep repeating. Right, so we've got car sent. We're calling the airdrop contract. We are calling claim, which takes as parameters an address, the uint256, bytes32 array, which is the proof, uint8, which is v, bytes32, which is r, bytes32, which is s. Now let's put all those parameters in. So the first one is the address that wants to claim, which is my second address. Then the amount, then the proof array. So we've got an array like this. And then in here, we want to be putting the proof. So let's get those proofs for my account. So we need to find that address. This is my address. So I need to get those two proofs, number 1 and number 2. And then we can get v, r, and s. Then we need -- account, updraft, -- rpc, -url, zk sync, Sepolia, rpc, URL. Enter my password. And it says we have successfully called claim, but let's check that. Let's run cast call on the token contract to check the balance of my second address. So we need balance of an address, function signature, and then the address is my second account. So let's copy that address, put it in there, -- rpc, URL. So the last time you're gonna have to do this. zk sync, Sepolia, rpc, URL. You can see it's non-zero. Let's do a little cast -- deck. Amazing. You can see that on ZK Sync, we have in fact claimed 25 bagel tokens for my second account using my first account to pay for the gas by signing a transaction with my second account to say, yes, my first account can call claim and have the tokens airdropped to my second account. Let's have a look at this on ZK Sync Scanner. So you can see in here, we have in fact got a transaction. 25 bagel tokens were sent to my account. It has worked. We haven't yet processed on Ethereum, so this is not completely final, but we can consider this as final because we're on ZK Sync and it's amazing. That was so cool. So now we can just wrap things up and give a brief summary of everything that we have learned. Okay, so in this module, we have learned what an airdrop is, what a Merkle tree is, and the fact that we can use Merkle trees to prove that some data is in a group of data. We can use it to verify that they are in fact in that data. We can use this to airdrop tokens without having to loop through an array. We have learned how to use signatures, how to create them using both vm.sign and cast wallet sign. We've learned how to use signatures inside our smart contracts and verify them using OpenZeppelin, which implements EC recover. And we've done this in a safe and secure way. We have tested our smart contract. We have created a script to deploy our smart contract and interact with it. We have then done that on Anvil, on ZK Sync local node, and then finally on ZK Sync Sepolia. We have learnt what different transaction types are, how signatures work, and how ECDSA works. There was a lot of information here, so don't worry if you feel a little bit confused. Don't worry if you're completely confused. Feel free to watch the whole thing again to read up some more, as always, as this was a lot of information and it was a lot to take in. But with that said, it's done. So, as always, time to take a break. Let this information solidify and come back to have some more Patrick fun. And I will see you very shortly and enjoy the rest of your course.